Until the last discussion, we covered MNIST. We discussed about MNIST in a lot of detail. We built a neural network on the MNIST data, and all of you recall that. So this was the case study that we did until yesterday. And using this as reference, we tried to do a lot of other case studies today. So this was the MNIST digit recognition data set that we worked on. And we also understood in detail about how machines understand images, how machines look at every image as a collection of pixels. Here you can see every image is like a 28 cross 28 uh, data set. So there are 784 pixels in each and every individual data set. That's the inference that we had, and there are 60,000 such pictures. Next up, we looked at building a Keras, use the Keras framework to build a model. This was the example that I showed you. We did lots of experimentations in the last discussion. You don't have to build such a complex neural network, because we discussed yesterday that if you have too many hidden layers and if you have too many neurons in each layer, then you will be prone to overfitting. So do not have too many layers. Start small, start with a good baseline, and then you can scale up from there. Don't straight away start out with a very, very deep architecture. Don't straight away start out with a very complex architecture. Start small and then scale up as and when you require. And we also looked at things like learning rate and other kinds of things. Few important things to keep in mind. There is something called categorical cross entropy. This is what we use for a multi-class classification problem, where you're trying to predict multiple classes. And in the output layer, we have used something called dense of 10 activation equal to softmax. So even when we fast forward to the Fashion-MNIST dataset, this is the solution files. I've shared all the solution files with everybody on the Google Drive. All the solution files are present here. You can look it up. So even when we come to the Fashion-MNIST dataset, this is the Fashion-MNIST dataset, right? I talked you through it. So this is effectively a dataset of different types of clothing articles. Okay, so just like MNIST, there are 10 classes. In Fashion-MNIST also there are 10 classes, but these 10 classes correspond to clothing articles. Okay, so otherwise the structure and the dimensionality of my data is exactly the same. Every image is 28 cross 28, and every image is a collection of 784 pixels, because if you do 28 squared, you end up getting 784. Okay, so this is the Fashion-MNIST dataset that you can see. We have pictures of t-shirts, we have pictures of trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, ankle boots. So these are all the different types of objects that we have. And the objective is to train a computer vision model to understand what each of these objects look like. Okay, to train a computer vision model. So build a model to identify the different types of objects, and based on that, you try to figure out what they are. Okay, so 10 classes is what you have here right now. It will be a slightly difficult compared to MNIST, because you can understand that there are some overlaps that you will have. For example, t-shirts and pullovers can look similar. So when you're building the computer vision model, or maybe let's say shirts and t-shirts, t-shirts and pullovers look kind of similar, or maybe sneakers and ankle boots look kind of similar. So when you're building the classification model, and especially when you are creating the confusion matrix, you might end up seeing some overlaps around these classes. So there might be cases where model predicted it's an ankle boot, whereas actually it's a sneaker. They look similar, right? Because remember, we are still using dense layers. We're still using fully connected layers for the modeling, which is a very basic approach. Coming to the architecture, the solutioning, initially we loaded the data from tf.keras.dataset. This is the default place where the dataset is already present. And next up, we are defining the architecture 28 cross 28 input shape. We are reshaping it. Why do we have to reshape the data? Because remember, the dense layers that we are using right now, they cannot work with two-dimensional data. So I cannot take a 28 cross 28 data, and I cannot use that in conjunction with a dense layer. So this is a mandatory pre-processing step where you take the original 2D data and you try to pre-process that into a one-dimensional flattened format. So this is the thing that we do. Then we do something called batch normalization. We did not see this yesterday. Batch normalization is a way of scaling. Okay, so what is a batch norm layer? Batch norm is a fairly new inclusion in the world of Keras. When I say new, it's still 10 years old. So this came around 2015. Neural nets have been around for a long time before that. But batch norm is a relatively new addition in the whole Keras framework. And all it does is it scales the data. It scales the data in between the layers. Because remember, if you go back to what a neuron does. What does a neuron do? In a neural network, there are tens of thousands and hundreds of thousands of neurons uh, that are playing out. So what is a neuron actually doing? A neuron is nothing but a computational unit. Y equal to W times X plus B. That is all that a neuron is doing. You're giving some inputs, the neuron is doing some processing, and it is giving some output. That is all that a neuron is doing. You give some inputs, the neuron will do some processing, and it will give the outputs. That's the whole idea. That's the whole idea how a neuron is inherently going to work. Okay. Now, batch norm, what it does is it takes that output, whatever output the neuron is giving, it is going to take that output and is going to intermediately scale it. It is going to scale that output. That is all that a batch norm will do. It will scale the output in the intermediate layers. Okay. Now, moving on, this is the architecture. You can again see we have reshaped it. We have done batch norm scaling. As a best practice, you should do batch norm after every hidden layer. It's a good practice because whatever outputs are coming after every layer, that is being scaled. Okay. And then dense of 200. Dense of 200 is like we are having a hidden layer with 200 hidden neurons present inside it. And dense of 200 means it's a fully connected layer. That means every neuron in that layer is connected to all the neurons in the previous layer. Okay, so each and every neuron in that layer is connected to all the neurons in the previous layer. So that is what we refer to as fully connected or dense layers. Then we use something called leaky ReLU. Leaky ReLU is an activation function. Yesterday, I was just using activation equal to ReLU, activation equal to ReLU. Now here, just from a code perspective, I wanted to show you that this is another way you can define an activation layer. So instead of saying dense 200 activation equal to ReLU, you can do that also. You can use it as a Keras layer. You can use the activation separately as a layer. So they are both equivalent things. The only thing is that there are different activation functions that we have. Okay, if you see this is something called leaky ReLU, it's a variation of ReLU. Okay, so there are different types of ReLU activation. The most basic one and the most widely used activation function is ReLU, what I showed you in the code yesterday. So this is just another variation I'm trying to show you. So don't worry too much about this, okay? Yeah. So now another dense layer, another dense layer, another dense layer, and the output layer is dense of 10 activation equal to softmax. This is as per what we covered yesterday. Nothing is different. As I told you, the architecture of my network is exactly the same. So nothing will change. And here I'm using an optimizer called stochastic gradient descent. This is the fundamental way how the neuron training or the neural network training is progressing. We talked about that deeply in yesterday's session. We looked at forward propagation, back propagation. We understood how by doing gradient descent, we are updating the weights and biases. We had a long conversation on that. And this is exactly what is how we are doing the gradient descent. The optimizer is controlling that. And we are starting out with a learning rate of 0.001. It's always a good practice to take a low learning rate. As a general best practice, you should always take a learning rate less than 0.1. Don't take a learning rate more than 0.1. And we saw some of the limitations of taking a high learning rate vis-a-vis a low learning rate. We saw that already. Now, model.summary. Always a good idea to, after you do everything, it's always a good idea to see the model summary to understand what is the input, what are the outputs. Also very useful for debugging. If something is going wrong, you always want to go back to your summary model and check what's going wrong. So this is a model summary, which helps you understand that, hey, we are taking 784 inputs, which are the 784 pixels in the picture, and we are getting overall 10 outputs. So everything looks good. We train the model over 20 epochs. It's all another very good practice is we always try to start small. Don't straight away say 100 epochs, 900 epochs, 1000 epochs. Don't do that because then it will take a long time for the model training to complete. And another good practice is that start small, start with 5 epochs, start with 2 epochs. Because at the very start of the neural network training, you want to monitor your network very closely. Okay, I told you, and I've been maintaining this right from the very first day that this entire field of AI and ML is a very experimental domain, right? You have to try out things and only then you will figure out. It's very experimental. You have to try out. There's no set rules. There's no set rules that, okay, epochs equal to 100 will work. No, you have to try out. You have to monitor. That is why Keras gives you a wonderful utility where you can run the epochs, you can see the progress, you can see how the training accuracies are improving, how the validation accuracies are improving. So this is the kind of mechanisms that Keras will give you. And this is what you, as a data scientist, you will have to use to monitor. You cannot just say epochs equal to 200 and forget. No, you have to monitor. You have to keep an active, you have to actively observe the overall training process and see At what point do I see overfitting is coming in? Now, there are better ways of doing it. I'm not saying that, you will literally stare in front of a computer screen and, see that, hey, my training accuracy is 84.65, 90.71, like that. No, I mean, there are better ways to do it. So you can effectively take this entire data over 200 epochs, and what you can do is you can, like, use a matplotlib to go and effectively visualize this data. Okay, you want to see what I mean to say? Want to see what I mean to say? So it won't be too hard to show you. And you must always use GPUs. Okay, I maintained this point yesterday. From here onwards, whatever demos we do today, you should always use GPUs, because the GPUs, they use the parallelized computing architecture. So, you're able to parallelly perform computations. Very, very important. Okay. So now let me quickly go and run the code. You can see this is what we have here: sequential reshape, and this is the model summary that we will get. Let me run the code, and what you can do is you can of course monitor the model over uh, 20 epochs, how it's doing. Okay, let me reduce it to 10. And as I told you, you don't have to explicitly go and monitor the model training. Okay, LR is actually an error because it's actually called learning rate. That's okay. These small mistakes, don't worry. So the terminologies have actually changed. It's called learning rate. And whenever you get any error in Colab, it's very easy to explain. You can click on explain error, and Gemini will often provide a solution. Right. So just wanted to show you, whenever you try out some exercises and you get an error, here I already fixed it. But if you get some exercises and you get some error, just click on explain error, and Gemini will understand the error in its context. It will look at the entire code that you have here. It will understand what mistake you're making. So no need to go to Stack Overflow and all that and check what mistake. You can see suggested changes. It will tell you exactly what it is. Anyways, I already did that before even looking it up. And then it will give you a code cell. And look at the best part is that it will actually give you the code cell with respect to what you have got. Can you see? Incredible, right? So you can literally just go and either copy and paste, or you can create a new cell. If I click on add code cell, see how I have added a code cell. Anyways, I already made the changes, but Gemini already, like, you don't have to like go and look up somewhere. It already gives you an entire ready-made code that you can write. Okay, it's one of the best language models out there, and part of the one of the biggest reasons why the current Gemini model, especially the 2.5 Pro model, does so well is because it has a very, very high context window. So in very non-technical terms, context window means how far it can remember. So if you have very large code bases, imagine you upload a this is a very basic exercise, I know, but imagine you have a very, very complex exercise, a very big Jupyter notebook. There are like thousands of lines of code. Gemini will still remember that. Okay, if you fire a Gemini within Colab or other interfaces, it will still understand your code base. It will still summarize all that you have written, and it will still give you solutions with respect to what you've got. Okay, so this is again some of the reasons why it's so powerful actually. This approach of using byte coding and all this is so powerful. Okay, so now let me run the code, and this is what we have here. This is the approach that we followed yesterday. The only difference is that I will not straight away go and like explicitly show this. Yes, I want to see accuracy and all that. This is what we talked about. I want to monitor the model, training accuracy, validation accuracy. But there is one other additional thing I'm doing. I'm saying history equal to. So what is the meaning of this? It means that, okay, let me go through the epochs. Let me monitor what are the training and testing accuracies, all that we will do. But let me also parallelly save the state of my model to the history object. Okay, this is the additional thing that we are using. And after the training is complete, what I will do, very simple. Okay, it's going to train in the background. I'll simply use Gemini generate AI. Right, this is the Gemini generate function that I can add, and I can say that plot the training, and you don't have to write so much. It'll just maybe 2 lines, and it'll figure out what you want. So plot the training and validation accuracies across all the epochs. You can even give it as a comment, and it'll still figure out. Okay, it'll understand the context. It'll understand your code, whatever you wrote before that, and it'll try to generate this for you. Okay, yeah. Uh, from the history object, I'm explicitly saying from the history. I'm trying to give it as much context as we have, and you can see that like if you don't know what is history, you cannot write this. This is what I meant. Like having a good understanding of the concept and knowing how to use these tools is a deadly combination. Right? So people who say that you can just use Gen AI and you can write code, no, that's not right. Because if you don't know what these things are called, what will you write? So you should understand these tools also. See, I know what is training accuracy, I know what is validation accuracy, I know what is history object. I explained to you right now. Now we can use it as a complementary skill. Okay, now it becomes a very powerful thing. See, so all I'm doing is I'm now taking the data from the history object, and I'm saying history.history accuracy and history.history val accuracy. And this is the way to plot a line chart in Python, right? So you can see this is the line chart, and this is how you can actually monitor the progress. This is what I meant. Like, you don't need to stare at the screen and you know uh, see what is my train accuracy, what is my val accuracy at every step, but you can simply like complete the entire piece. After the entire training is complete, you can save your results in the history object, and you can monitor. You can monitor, and I think you're getting a very good understanding that the model is continuing to learn. There's a very strong, there's a very strong uh, learning that is happening. So the learning has not stagnated. That's the important part. So initial epochs, obviously, the learning was very strong, and as we go to epochs 10, the learning seemed to have slowed down. But the validation accuracy, the testing accuracy is still increasing. There's still an increasing tendency. If I try to extrapolate this, there's still maybe 2-3 percentage points more I can go. And these are the kind of experimentations that you will have to do. And that's why I always say I've maintained this part right from the day one, that building a POC is the easiest part. Right? You work on a data set, and we'll do that brainstorming exercise today. We'll look at lots of case studies and all that today. But you have a data set, you have a use case. You can absolutely brainstorm, and it's very easy to come up with a baseline model. Anybody can build a basic Keras architecture, and you can build a baseline model. But what is the most painstaking part, and the thing that will take weeks of effort, quite literally weeks. I'm not underestimating. It's weeks. Okay. uh, Sorry, I'm not overestimating. It's weeks. It will be more than that. You will have to fine tune the model. So this part is the most painstaking part. It could be about adjusting the learning rate, adding some layers, adding some dropouts. Maybe if you see overfitting happening, how do we get that extra 1 or 2 percentage points more? Because that 1 or 2 extra percentage points of accuracy can mean it can translate to millions of dollars of savings. Right? You relate it back to the call center use case. Remember, we did that lead scoring case study, beautiful case study where we were looking at the different attributes of a lead, and we were trying to predict whether the lead will convert. Okay, so only the customers who are likely to convert, we will call them. And there are a lot of these kinds of so-called customer-centric chatbots that are getting deployed today. Entire call centers are getting transformed today as we speak due to generative AI and some of these, integration of AI and machine learning into their processes. It's very real transformation that's happening today. If you think about it from the business perspective, it is dollars. It is dollars of savings, right? So if you're able to get a model which is more accurate, that straight away translates into dollar savings for them. Because if I am able to accurately identify customers who are likely to convert, then that's a big thing. If I'm inaccurate, if make end up having too many false positives, too many false alarms, you're ending up calling to like, then it's a loss for the business. So 1 or 2 percentage points high accuracy straight away converts into tens of thousands of dollars saving for the business. You need to keep that at the back of your mind. So why are we putting the weeks of effort after we build a baseline model? It is for those kinds of things, and customers will want to see that. When you go and present explainable AI, when you try to present a dashboard that, hey, this is the machine learning model we built and this is what we got, you will have to present in that term. You'll have to build a confusion matrix. You'll have to show them, like, this is the number of false positive, false negative, and that is how we will define an acceptability criteria. Okay, these kinds of things we will get. All right, now moving on to the next exercise that we talked about. This is the CFAR 10 one that mostly everybody has also completed. And what is the CFAR 10 dataset? Again, it's a very real world dataset, involving 60,000 images. The only difference of CFAR 10 with respect to the other datasets that we worked on is CFAR 10 is actually a colored picture. This is based on colored images. Okay, so this is based on colored images. So each and every image is 32 cross 32 cross 3. So this is the data set that we have. Every image that we have is 32 cross 32 cross 3. And this is the colored images that we have right now. Okay, and there's 60,000 such pictures that we have. But otherwise, the architecture will be very similar. There are 10 classes that we have here, very similar architecture. And there are 60,000 images, each image 32 cross 32 cross 3. That is the CFAR 10 data set that we have here overall. Okay, and very similarly, we are solving this problem now. You can see we are loading the data, default data, and the only difference, the biggest difference in this part of the code will be this part. Okay, you cannot directly copy paste. This is the only change you have to make. See, we have taken 32 cross 32 cross 3 and we have reshaped it into 3072 pixels. So this is the only change that you had to do when you are working at your end. Okay, and why 3072? Why did we do this? Because we have to flatten the data. Remember, we cannot work with two-dimensional data. We cannot work with two-dimensional data. We have to flatten the data. So we cannot work with 32 cross 32 cross 3. Fundamentally, we cannot work with 2D data. We have to flatten the data and only then we can work with it. So if you do the computation, if you take 32 into 32 into 3, if you do the computation, you will actually get 3072. So we have 3072 pixels. The input we have flattened it to 3072 pixels, and then we add our dense layers and other things, and we go about it. Otherwise, things are very similar. Very similar. We have added batch norm for scaling. Again, dense layer. Again, batch norm, and you can see we have multiple dense layers. And at the end is the same. The output is very similar. Dense of 10 activation equal to softmax. Other parts of the code are exactly the same. No difference. And if you see, we have trained the model over 10 epochs, 20 epochs, and we are getting around 53% accuracy. Okay, and this is the thing I wanted to highlight, that there's a very drastic reduction in the performance compared to MNIST and Fashion-MNIST. The reason is because there's a color pictures and they're harder to classify. And there are better ways of doing it. And we'll discuss that. What other architectures can be used? How else can you solve the problem? If this is not the right way to solve the problem, how else can we do it? What is the better way to get higher accuracies? And we'll see that. On the same data set, I will show you how you can get very, very high accuracies, and we'll see that. Okay, but iteration 1, we are getting only around 50%. And you can see that beyond the point, even if I increase the epochs, beyond the point, even if I increase the epochs here, we are still seeing that beyond the point, even if I increase the epochs, you're seeing that there is no noticeable improvement in accuracies we are getting. The accuracies continue to be round about the same. There is no noticeable improvement in accuracies we are getting right now. That is the way we are able to observe this. Accuracies remain the same. See, we go from epochs equal to 4 and you go to epochs equal to 20. See, the accuracy, the validation accuracy is still around the same. So that is the observation that we can make out. Next up, CFAR 100 will be very similar. People who solve CFAR 100, I'm sure you're reporting accuracies which are lower. Accuracies of CFAR 100 will be comparatively lower than CFAR 10 because I told you conceptually, the more the number of classes, if you have more number of classes, it is harder to classify. In CFAR 100, very similar data set. If you go to this link, this is the link I already showed before. If you see, this is CFAR 10, there are 10 classes of objects we have, very broad categories, still kind of easy. But if you look at CFAR 100, there are 100 categories. So within reptiles, there are like 5 different types of reptiles. This is a harder data set. So we have like 20 super classes. These are the 20 super classes, and within each of the 20 super classes, we have 5 subclasses. So let's say if you have fish, within fish, you've got each of these cards. So broadly, given a picture, the model has to classify 1 out of these 100 classes. This is a harder problem because we have more classes, and because we have more classes, there will always be a higher chance of overlap. There'll be a lot of cases where model predicted something, actually something. So the confusion matrix will again be very, very useful in these kinds of problems. So CFAR 10, CFAR 100, I think you would not have got more than 25, 30%. This is what some of the folks mentioned also. So if you try to do your CFAR 100, ANN model, you will not get more than 25, 30%. Okay. And another thing I want to clarify, these are all called ANNs, okay? There's a term called ANN that I'm using. What is ANN? ANN stands for Artificial Neural Network. This is the most basic form of neural network that we have discussed until now. Okay, this is the conversation we had until now. All of what we talked about, the foundations, everything boils down to ANN. This was also the same video that we discussed yesterday on Andrew NG, right? He explained dense layers, how we can add new. So this is the fundamental idea of a neural network, and this ANN stands for Artificial Neural Networks. The conversation that we have going forward, we will talk about different types of neural networks like CNNs, RNNs, and so on and so forth. Okay. So then we did the diabetes case study. The diabetes case study was based on a structured data. And you can see this is a very similar problem that we already did before when we work with sklearn framework, the traditional machine learning framework. We have the 8 different features of a person, and based on the 8 different features of a person, we are trying to predict whether the person is diabetic or the person is not diabetic. So it's the outcome that we are trying to predict. So based on the features of the person, we are trying to predict, is the outcome 1? That means, is the person diabetic, or is the outcome 0? Is the person not diabetic? So that's the problem that we are actually trying to solve. Okay, you can see that we have done these things already. Pair plot, looking at the class separations, feature importance, all these things we already did. We already did all these things, you can see. And this is building the graph in Keras. This is what we have here. And these are the things we already did. And this part is the same. The only difference really here would be with respect to the output layer. You can see that the loss function here we have is binary cross entropy. So what is the loss function that we have here? The loss function we have here is binary cross entropy. So that is the loss function. And the output layer is, we have got dens of 1 activation equal to sigmoid. Okay, so we have dens of 1 activation equal to sigmoid. So this is a sigmoid activation function that we are using right now. Okay, so dens of 1 activation equal to sigmoid is what we are explicitly using. And so all that we are doing in the output layer is we are trying to predict what is the probability it is diabetic and what is the probability it is not diabetic. So that is what we are trying to predict in the output layer. That's the inference. And this part is again very similar. The only change would be, as I said, the output layer, because whenever we are doing binary classification, we will not use softmax, because softmax we are trying to predict multiple probabilities so that they all add up to 100%. But in but binary classification, we only are trying to predict a single output. This is the biggest difference, right? If you see the previous case studies, we were saying dens of 10, but here we are saying dens of 1. The output layer is only 1. You are only trying to predict a single answer. That means a single value you are trying to predict, and that value will be a probability. Okay, so the probability will be between 0 and 1. So if you look at a model summary, the neural network would be like, we have 3 inputs. Why 3? Because we have only taken the 3 most important features. We identified the pair plot, we identified the feature importance. We took only these 3 features now: glucose, BMI, and age. And so input layer, if you see there are 3. Reshape is 3 we have done. And then you pass it through the hidden layers, and the output layer is dens of 1. So we are trying to predict the probability of a you can see that based on the features, we are trying to predict what is the probability the person will have diabetes. So it's the probability value that you're effectively trying to predict. Either the person will be diabetic or the person will not be diabetic. Couple of other things that we have used in this solution file. We have used something called a Keras checkpoint callback. What is the Keras checkpoint callback? Checkpoint callback is a way to save the state of your model. Okay, at different phases, you can use the Keras checkpoint callback to save the state of your model. Okay, you can save the state of your model. You can use a checkpoint callback to save the state of your model. So here also, if you see, we define a checkpoint file path. This is the checkpoint file path that we define, and we define a checkpoint callback, and we are saying, oh, keep monitoring the validation accuracy at each and every epoch. Please keep monitoring the validation accuracy, and only save the best model. Save best only equal to true. This is what we do in a checkpoint callback. So we, at every epoch, as the model is getting trained, we will continue monitoring the validation accuracy. We will continue monitoring the validation accuracy. And whenever the validation accuracy is increasing, we will save the best state. And what is the reason? What is the reason why this is important? Because I'm sure you would have observed that during the neural network training, there are a lot of instances where, if I take you back to the last demonstration, let's say the CFA 10, or maybe any one of them, maybe CFA 10 ANN that I just now showed you a while back. So if we just look at it, as you go through the epochs, it is not guaranteed that the val accuracy of the last step will always be the highest, right? Now here apparently that is happening, but maybe if I take you to another one, maybe if I take you to Fashion-MNIST or even MNIST, this was the most basic demo that we did, MNIST, right? So the last epoch is not guaranteed to give you the best answers, right? The last epoch is not guaranteed to give you the best answers. That is the important part. So whatever last epoch we are having, it is not guaranteed that the last epoch will always give you the best answers. Epoch number 1 can give you some validation accuracy. Epoch number 2 can give you some other validation accuracy. And epoch number 3, the validation accuracy can be something different. Okay, there can be changes. There can be changes, right? Even if you see the diabetes one, if you observe, initially epoch number 1, the validation accuracy was this. And if you go all the way down to epoch number 100, I've done 100 epochs. Epoch 100, the validation accuracy is only 77.92. But remember, we are saving the checkpoint callbacks, right? So at some epoch, we saw a validation accuracy of 81.818%. This was a validation accuracy we got. We got a validation accuracy that was 81.818%, right? This was an accuracy we got. This was the overall validation accuracy we have right now. That's the inference, right? So somewhere during the model training, as we trained the model over multiple epochs, we found that the validation accuracies were high. So you can see the epoch number 10, validation accuracy 70%, epoch number 13, validation accuracy. So at every point when the model is improving, see the validation accuracy improve from 69 to 70. So saving the model to the checkpoint callbacks, checkpoint file. It's nothing but a simple checkpoint file. Think of it like, whenever you update, you're updating your Word document. You're updating, you're keeping a save point like that. So whenever the accuracy is improving after every epoch, you're saving. And whenever the accuracy does not improve, like let's say until the 12th epoch, we are getting how much? The 12th epoch, we are touching 77.27, right? The 13th epoch, it did not improve, right? The 13th epoch, if you see the validation accuracy dropped. It was 77 in the previous step. Now it has dropped to 74.03. It did not improve. And it can happen, right? Because what is the concept? The concept is weights and biases. The next epoch, maybe the weights and biases were updated in an incorrect manner. It can happen. There can be some fluctuations that can happen in the neuron training. It's very normal. It's a very normal thing. But we don't want to update it. So because the validation did not increase, what we will do is we will not save that model back to the thing. So you can see validation did not improve from 77. So we will not save it in the checkpoint file. So you continue doing this. I think somewhere we would have touched 80. Can you see we are touching 81? So now we are again saving, improve from 77 to 81. So saving the model to the checkpoint file. And you will keep doing it. You will keep doing it. Again, I think it improved from 81.16 to 81.81. You'll again save it in the checkpoint file. And I think this was the last update that we have. Until the end, there are no other updates. So this is a very important thing, because as you continue to train the model across hundreds and thousands and tens of thousands of epochs, these are some very automated ways how you can effectively save your best model. And at the end of your model.fit, after the model.fit completes, what you will have, you will save this model. And what will be the saved state? The saved state will not be the last one. The last epoch is not what will be taken, because every step, every epoch, you're having a different set of weights and a different set of biases. So the final epoch will not be considered. What you will consider is the best epoch based on the best validation accuracy. That is how it will be done in the real world. Okay, so this was the diabetes case study that I talked about, and very similar to that, we actually solved the loan case study. The loan case study is what we solved, very similar to that. Idea is exactly the same. Again, the whole objective here is to show you how we can work with structured data. Okay, all this while we have worked with pre-built data sets. Okay, how can we work with the same kind of structured data that we have discussed all this while in the course? Okay, so here also we have the different attributes of the borrower. You're trying to apply for a loan, you're trying to borrow money, and based on the different applications of the loan, the features or the different attributes of the loan, you will have things like how much money you want to borrow, what are the interest rates, where do you stay, what is the purpose, all that kind of stuff. And based on that, the model is trying to predict, based on the features of the loan application, the model is trying to predict, will you fully pay the loan or not? This is the output column. The last column is the output column. So based on the features of the loan, we are trying to predict, will you repay the loan or not? Will you repay the loan or not? This is the problem that we are trying to solve. And we are approaching this the same way. Nothing much to discuss. We are approaching this the same way. We can do the pair plot. We can do the correlation. We can see a feature importance. Feature importance is a great way to identify upfront what the important features are. This was a very, very important way how we approached ML problems before. But honestly, to some extent in deep learning, this is not that important, because in deep learning, the feature engineering is a lot more automated. right? So unlike in machine learning where you will straight away outright reduce features, you will straight away drop the features which are not important. In deep learning, maybe not. I mean, if you see that some features are absolutely nonsensical, you can drop it upfront. But otherwise, generally, as a best practice in deep learning, we don't manually reduce features, okay? Because we let the network do it. And that is again one of the major differences between machine learning and deep learning. Because in machine learning, the pre-processing part is very manual. You will have to pre-process your data, scale it, transform it, encode it, all of those kinds of things we talked about, right? But in deep learning, the network will take care of the features. And every feature, if you remember, as it propagates through the neural network, as you know, every feature is effectively assigned weights. You're doing W1 times X1 plus W2 times X2 plus dot, dot, dot. Your every feature is assigned weights. So the network, as part of the gradient descent process itself, you know, if it thinks that a particular feature is not important, if the network thinks that a particular feature is not important, it will automatically downweight that feature. It will reduce the weights against that feature. So let's say you're training the neural network right now, and you observe that a particular feature is not at all important. A particular feature is not important for me to associate my x's with my y's. Okay, so you don't have to outright remove it manually. So the network itself will figure out the feature has no weightage. It will automatically reduce the weights. So as part of the gradient descent, the weight for that feature will come very, very close to zero, or it might even become zero. It never exactly becomes zero, but it will become like 0.00000 something. It is almost like an insignificant feature in the overall prediction. Okay, so that is another very important concept I wanted to reiterate. I've already mentioned that, wanted to reiterate that. Okay. Anyway, so this is the pair plot and all that we have seen, and this is the network. This part is very similar, train test split. We have 12 features. I'm taking all the features. I told you I'm not dropping anything, okay? Except for the output, that one hot encoded column. There's a categorical column I told you, like if you want to encode it, you can. But just for simplicity, I did not want to get into encoding and all that in this exercise. I just removed that column for simplicity. But in practice, you must encode your categorical features as well. Because if your data has strings, if your data has something which is not a number, you will get errors. That is true in sklearn. That is also true in keras, because all these are mathematical approaches, right? So they cannot understand strings. So this is an example. This is an example, but I think I mentioned this to you yesterday, that don't try to take dense of 2000. These are very, very big layers. Don't try to take that. If at all you think that you want to use lot of hidden features, then distribute it across several layers, right? So this is not a good practice. The intent of showing this example is to tell you that, hey, this is the way you should not do things. As part of the best practice, you should not say dense of 2000. If at all you want to have lot of hidden neurons and lot of hidden features, and you want to learn the patterns based on that, what you will do, you would rather distribute this across several layers. You will take dense of 100, dense of 200, dense of 500, dense of 1000, something like that. You will eventually add up to 2000. But instead of saying 2000 in one go, rather you distribute this across 4 layers. Okay, so the idea is to build a deep architecture, because then only you tend to learn the hierarchy of features. The learning from one layer will go to the next layer. Instead of learning everything in one layer, this is inefficient. Instead of that, you distribute the learning across several layers. Okay. The rest of it is exactly the same. Nothing to talk about. Dense of one, activation, sigmoid. Why? Because this is binary classification, and you can see the accuracies. Mostly everybody would have done this, and the scores are coming something very similar to diabetes. It's not very good, uh, and you have to keep this also at the back of your mind. Beyond the point, deep learning will not, help me build an excellent model. No, I mean, there are limitations to deep learning also. Beyond the point, there is nothing you can do. If your data is bad, your models will be bad. Okay, if the quality of my data is bad, the models will be bad. There is nothing we can do about it. So deep learning inherently will, will not give me good results. And here you can see that even if I train the model for 20 epochs, 30 epochs, 40 epochs, you can see that the training accuracy itself is kind of stagnant, right? It's one thing to say that the validation is reducing and all that, but here even the training is stagnant. So there's a lot of work we need to put on it. We need to maybe go back and adjust the network, use some different hyperparameters. A lot of tuning needs to be done. And these are the parts where we get stuck. These are the parts that will actually take a tremendous amount of time. I know when I'm saying this, it sounds very simple. Like, you might say, okay, so we will try, we'll increase the accuracy. But when you do this in practice, this is the hardest. Trust me, the POCs are very easy. You can, get it up and running in a matter of seconds. right? But the hardest part is to, take that 84. I challenge you. I challenge anybody who can do it in the class. I don't know what award to give you, but well, like, I challenge you. You try to take it up to 90%. It's impossible. It's impossible. You cannot do it. You try what you want. You spend a month's effort. You cannot do it. So these are the challenges. Now, of course, like there are ways we can do transfer learning and all. We can, try to figure out. But beyond the point, you cannot improve the accuracies. And these are the challenges. That's why it takes time. That's why it takes so much time to train these neural nets, to tune the neural networks. Okay. Now we will get into a very, very interesting conversation. So far, we have discussed about ANNs. So far, we have discussed about artificial neural networks. We have discussed about neural networks generally. We talked about neurons. We talked about a network of neurons, how we stack them in layers and all that. So we talked about neurons generally. Now we will get a little deeper into a very specific class of neural networks called CNNs. We'll get a little deeper into what are CNNs. What are convolutional neural networks? So what is the inspiration behind this topic? Why are we discussing something? See, because when we learn something, like it's not as if we are just learning it. We should understand why we are learning, right? All this while we have learned a lot of things. So you might be wondering, okay, why are we learning something new right now? Why are we learning CNN? We already know neural nets. We already know keras. So what is the reason we are learning CNN? CNN is a very special type of neural network. They stand for convolutional neural networks. See the term CNN I've used? They stand for convolutional neural networks. And they are very well suited to work with pictures. CNNs are very well suited to work with image data. The kind of thing we discussed until now is something that does not work that well with, I'm just going to come, just give me 1 minute, just going to complete and come, is something that will not work that well with images. We have discussed normal dense layers. We've discussed normal neural networks, artificial neural networks. So now we are getting into a very specific type of neural networks called convolutional neural networks that will work very well with pictures. Because you saw, right? You saw that in MNIST and Fashion-MNIST and CFAR 10. CFAR 100 was, I think, a very good example. CFAR 100, some of you tried out and you got like only 20%, 25%, 25% validation accuracy. Like that's worse than a coin toss, right? Actually, not quite because because there are 100 classes. If you look at probability wise, it is actually 1 by 100. So that's okay, anyways. So, but you can think of it. Let's say CFAR 10, we got a very low accuracy, right? Only around 40%, 50% accuracy with a basic ANN model. So now when we do this with CNN, and I want to show the end result to all of you. Like this is the same exercise we can do with CNN, Fashion-MNIST, CFAR 10. When you apply CNN on CFAR 10, you will magically get 75%. The accuracies will just jump. You try to apply CNN on CFAR 100, and the accuracies will go up to 40, 50%. Why? We will see. So what is special about this kind of neural network? What is different? They're still neurons, they're still hidden features. Everything is the same as what we discussed yesterday. Nothing is changing, but there are some new ideas that we will try to learn. What is special about a convolutional neural network that they work so well with pictures? So as we delve deeper into the computer vision part, now we are getting deeper into computer vision. So we will see that this kind of network is going to get used a lot. Okay, convolutional neural networks. And computer vision is that field where we are trying to study and analyze pictures and anything to do with images and videos. Okay, so it has to do with image classification, object detection, so all the applications you see around you in a day-to-day life where you are interacting with images, you're interacting with videos. That's the use case we are talking about here. And that's what CNNs can help us process. Okay, so now what are convolutional neural networks? What are CNNs? So far we have seen ANNs. So far we have seen artificial neural networks or dense layers in the session so far. So what are convolutional neural networks? What are CNNs? And why is it that we need a different kind of neural network to process pictures? Because that was the high level understanding that we had. That was the big picture understanding that whenever it comes to image data, we need a different kind of neural network. The existing neural networks that we had were not good enough to analyze pictures. The existing neural networks were not good enough to analyze pictures. So we need a new kind of neural network to help us analyze images. So what is special about pictures? What is special about pictures? Let's see. When we look at an image, we humans, we look at an image like this. We look at the picture on the left hand side. Machines will always study images as pixels. We talked about that yesterday. We looked at MNIST, Fashion-MNIST. We looked at pixel intensity values. So machines will always represent this picture as pixels and analyze it. Let's take an example of a particular pixel value 180. So let's say we are looking at a specific pixel value which is 180. How do we understand what are the pixels around 180? What are the neighbors of the pixel 180? So when you look at this specific pixel which is 180, what are the neighbors of this 180 pixel? The neighbors of the 180 pixel will be somewhat like this, right? These are the neighbors of the 180 pixel. So what it means is, let's say you're looking at the, the eye of the bird. This is the 180 pixel stands for the eye. So when you look at the neighborhood around the eye, we have all the pixels around the eye, right? We have got the pixel 27, pixel 90, pixel 100, pixel 143, pixel 195, 190, 180, 99. So we have got all the pixels around the eye pixel. So this is the eye pixel that we have. And these are all the pixels that are surrounding the eye pixel. We have all the other pixel values which are surrounding the eye pixel. That is what we have right now. So let's say, for example, we are looking at the pixel which is 27, right? We are looking at the pixel which is 27. Now, very clearly, you can see the pixel 27 is very close to the pixel 180. So it is diagonal, right? And, and that's the way how we understand pictures also, right? When you look at how a human being looks at an image, we are looking at things in a very spatial manner, right? Isn't it? Spatial manner means we are looking at this kind of spatial positioning of the pixels. The spatial context is very important, right, friends? What is the spatial context? The spatial context is very important. How? Okay. What is the pixel that is near this? What is the pixel that is near this? What is the spatial context? Now, the problem is the moment we flatten the data, which is what we had to do for dense layers. So FC layers can work only with vectors as input. We talked about that. We talked about, dense layers. You have to flatten, right? Remember, we had the 32-32-3 picture for CFA10, and we flattened it, right? They can only work with vectors as input. So the moment we flatten the data, what will happen? The moment we flatten the data, what will happen is the spatial context completely goes for a toss. If you look at this image right now, remember how 180 and 87 were very close? 180 was here, 87 was here. They were diagonally opposite, right? The moment you flatten the data, the moment you flatten all the pixels, 180 is here and 27 goes all the way here. This is the biggest limitation when you're working with images. So when you look at a set of pixels which represent the original picture, and when you flatten those pixel values, when you go and flatten all those pixel intensity values, the entire spatial positioning of the pixels completely goes for a toss. The spatial positioning of the pixels completely goes for a toss. So pixel 180 will come all the way here, whereas pixel 27 will go all the way to the left. So this is where pixel 27 will be present. So there goes pixel 180, there goes pixel 27. That's the inference we will get right now. That's the idea. That's the problem that you will face. And this is the reason why when you are using dense layers, when you're using normal dense layers, or when you're using normal fully connected layers, we are getting a very low accuracy. Okay, when we are using normal dense layers, when we are using normal fully connected layers, the accuracy of the model is low. The accuracy of the model is coming out to be comparatively very low when we are using dense layers or fully connected layers, because the spatial information gets lost. And now when we use that network to classify pictures, when we look at an image and try to predict what is it and what is the class of the image and all that, when we try to classify images, it will not give us the right answers, because as I told you, the spatial positioning completely got disrupted. And this leads to a new kind of neural network called a convolutional neural network. It is still based on the same principal ideas of neurons and hidden layers and other things. Nothing changes. The only difference is this is a special kind of neural network that is meant to work with images. So convolutional neural networks work with pictures. right? So there's a huge amount of theory that we have here with respect to what happens, how it happens. All that is really not relevant for us. But what I want to show you at a very high level is the broad architecture of a CNN, what a CNN architecture looks like. This is what the broad architecture of a CNN basically looks like. This is how it, where it boils down to. So next time when you think of a convolutional neural network, this is basically what is it. On the left hand side, we start with a normal picture. The normal picture is, let's say, your typical CFAR 10 32 cross 32 cross 3. On the left hand side, you have the original image, which is 32 cross 32 cross 3. It's a colored picture, remember. So there are three channels, red, green, and blue. And you have the pixel intensity values for each of the three channels. So you have the pixel intensity values for red, the pixel intensity values for green, and the pixel intensity values for blue. So you have the pixel intensity values that are there for each and every individual channel. So you take that original picture on the left hand side and you process that picture. How do you process that picture? You pass it through multiple convolution layers, convolution ReLU, convolution ReLU, convolution ReLU. ReLU is the activation function. So you take the original picture and pass it through multiple convolution layers. And the convolution layers are basically extracting information about the picture. So all that you're doing is you're taking the original image and you're trying to extract features out of it. That is what the convolution layers will do. You are looking at the original image, which is coming on the left hand side. And from the original image, you are passing that original image through all the convolution layers. You are passing that original image through the convolution layers and you're extracting features of the image. So convolution layer 1 will extract a certain set of features. Convolution layer 2 will extract a certain set of features. And convolution layer 3 will extract a certain set of features. You take the original picture and you pass it through those convolution layers. Then we do max pooling. Max pooling is like a regularization. So convolution layers are basically, think of it like hidden layers. So from a concept and analogy perspective, there is no difference. Just that there is a lot of maths that is going on behind the scenes, which is not in our scope to talk about right now. We'll not get into the theory and all that for all that's useless right now. We'll look at the applications actually. So this is just like a hidden layer. So at a high level, think of it as if we are taking the picture, passing it through the convolution layers, which are like hidden layers. And each of the convolution layers are extracting features of the picture. You recall that beautiful example that we saw yesterday, that video from Andrew Ng where he depicted how the machine is processing the picture. So we take the original picture and we pass that original picture through the convolution layers. And each and every convolution layer is extracting certain intricate details about the picture. The layer 1, we were able to learn very basic features like shapes, diagonals, and all that. Layer 2, we learned slightly more advanced features. And layer 3, we learned slightly more advanced features. So each and every convolution layer, we ended up learning deeper and deeper features, which were coming in each and every convolution layer. And then we have something called max pooling. So then we basically have something called max pooling, where we go ahead and we try to regularize the overall network. Okay, so we use something called max pooling, where we try to, in a way, we try to regularize the network. That is the whole idea of what we, try to do as part of regularization. The end result of what we are trying to do in convolution, is we are trying to extract the features of the image. So you take the picture, you pass it through multiple convolution layers, and the end result of what you're getting is you're trying to extract the features of the image. And now that you have the image features, what you will do? Now that you have the image features, you will go and pass it through a fully connected layer. This is the dense layer, because the dense layer is what you will anyways use for the normal, this is what you will generally use for the normal classification, right? We talked about it. If you want to ultimately classify the images, this is your dense of 10 activation equal to softmax. Something very similar to that we will do. So this is how the architecture of a CNN broadly looks like. You can just think of it like a hidden layer. You can just think of it like, it's just that we use a very special term called a convolution layer, because there is a whole lot of math that is working out, like convolution operations, filters, and a lot of other things are working out. But at a high level, at a conceptual level, from a practical perspective, this is all that we are doing. We take the picture, we pass it through the convolution layers, we extract the features of the image. So we find out what are the different features in the picture. What kind of shapes do we see in the image? Do we see a line? Do we see a curve? Do we see a color patch? So we go through the picture and we try to extract the different features in the image. And then after we have extracted all the hidden features in the picture, now we go and apply a dense layer. We apply a dense layer at the very end. Okay, and in that dense layer, we try to predict what are the probabilities of the outputs. So we use a dense layer at the very end, and in that dense layer, we try to find out what are the probabilities of the outputs. What is the probability it's a cat? What's the probability it's a dog? What's the probability it's a car? And so on and so forth. Okay, so that's the way how we go about and look it up generally. Now, in the context of the MNIST dataset, we can plug this architecture for the different the different use cases that we have here. So now we can absolutely work with this architecture for the different use cases that we have here, generally speaking. And it's very simple. The idea and the the application part will be comparatively very simple, and we'll see that. Okay. Now, one important thing that I want to clarify, one very important concept that I would like to clarify, especially when you're working with CNNs, is that the features that you're extracting, because remember I told you that in each and every layer you're extracting features. The features that you're extracting will be very similar, right? There'll be very similar features. Okay, so the initial layers, like when you think of the hidden layers, the initial layers will extract very basic features. So the initial convolution layers will extract very basic features from the picture. Okay, so the initial convolution layers, the kind of features that they extract will be very basic features. And as you go deeper and you look at more advanced layers, those advanced layers will extract more and more advanced features from the picture. So that is what the features basically refers to. And features, as I said, could be anything. It could be different types of color patterns, patches, lines, horizontal lines, and all that. So this is what the features of the image will basically be. Okay, and there are ways to visualize it. I will show you what are the different ways you can visualize it and all that. We'll see that as well. Okay, this is the very basic hands-on with respect to how CNNs will be done. So you can see this is a simple hands-on with respect to MNIST. So the initial part is exactly the same. Nothing changes. Nothing changes. Only thing is that you come here, reshape. You don't flatten it. You keep it as the same 28 cross 28 cross 1. Why is it 28 cross 28 cross 1? Because the width and height of the picture is 28 cross 28, and 1 because it's a grayscale image. There is only a single channel. If this was CFAR 10, we will use 32 cross 32 cross 3. We will not reshape it. That is the biggest difference. Otherwise, from a practical part, there is no difference here. And you can see here, we are just using the convolution layers now. Okay, you can see these are actually defaults. Kernel size, again, are slightly mathematical ideas, but you can safely take it as a default. Kernel size is actually a filter size. It's 3 cross 3 is a default, very much the default, you can use it. Activation value, we understand. And this actually tells you this is like equivalent to your dense of 32. I'm saying equivalent, not the same thing, but this is like equivalent to dense of 32. So conv 2D32 basically means that you are taking the picture that is in the previous layer and you're extracting 32 features out of it. You are trying to learn 32 hidden features or 32 new features from that original picture. This is very much like adding a hidden layer with 32 neurons. Think of it that way. Then we have another hidden layer with 64 neurons. Then we have another hidden layer with 128 neurons, and so on and so forth. So this part is exactly what we already understand. Just instead of dense, we use conv2D. And then we flatten, because remember, before we use the dense layer has to be used for classification. Classification, we need to use the dense layer. So before we use the dense layer, we have to flatten the intermediate outputs. So we do a flatten. Flatten will, flatten the intermediate thing, and we will now apply dense of 10. Rest of the parts are exactly the same. Nothing changes. If you look at the model summary, I think this will give you a better picture of what's going on. So we start off with 28 cross 28 cross 1. And then we pass it through batch norm, convolution, max pool, convolution, max pool. So this entire block that you see here, starting from convolution to this thing, this entire block is taking the picture. It is taking the resultant two-dimensional picture, actually 3 because there are 3 channels. We're taking the entire 3D array or the 3D image, and we are trying to, effectively extract the features of the image. And once we have the image features, we are now doing a flatten. Now we are flattening the image, and so you can see this is like 256 per 4 cross 4 cross 256. So flatten basically means you take this 4 into 4 into 256. So when you do 4 into 4 into 256, you get 4096. So we flatten this into 4096 pixels, and using that we will try to find out the 10 class probabilities. What are the probabilities of each of the 10 classes? So what is the probability? It's a, it's a 0, it's a 1, it's a 2, it's MNIST, right? So we're trying to find out the probabilities of those individual classes. That's it. Otherwise, everything else is the same. CNNs will be a little bit more compute intensive. I mean, if you run the code, you will see that the computation will be a little slower comparatively, but otherwise you will get phenomenal accuracies. Otherwise, everything else that we talked about, model compile, cross entropy, callbacks, we didn't use callbacks here, but all of those core ideas remain the same. We can save the model.fit to a history object, history equal to, we didn't do that here, but all of those ideas, the foundational ideas that we covered, overfitting, overfitting, underfitting, how do we monitor the epochs, right? So all those fundamental ideas remain exactly the same. Only thing is that we have used a convolution layer as a hidden layer, and we can see the accuracies are phenomenally high. Okay, so MNIST we touched close to 97% yesterday. Beyond that, we were struggling. So beyond 97%, we were struggling yesterday. We were not able to get it beyond but beyond 97% yesterday. So the moment you go and use CNNs, you see a drastic improvement in the accuracy. So straight away in the first and the second epoch itself, look at it. Epoch 1 itself, you're touching 99%. That's incredible, right? So epoch 1 itself, you're getting 99%, which is very, very good. Example number 2, we are using Fashion-MNIST. Rest of the parts are very, very similar. Nothing to talk about here. We're taking the same data. Only difference is we have not flattened it. We have not flattened it to 784. Otherwise, batch norm. And here, instead of dense layers, we are using convolution layers. The architecture is exactly the same. And you can see this is what I meant. We use batch norms after every hidden layer so that we are able to scale the outputs of the intermediate layers. Then we do a flatten, and then we do a dense of 10 activation equal to softmax. Sometimes it is also a good practice to add these extra dense layers. I've not done that. I've commented this out, but the idea of these additional dense layers is to introduce some additional learning, right? You can like whatever features are extracted after the convolution layers, before you do the final classification, before you go to dense of 10 activation softmax where the final classification will happen, it is a good practice to add some extra dense layers. Okay, so this is just for some additional learning, but be very, very mindful. The more layers you add, the more your model might be prone to overfitting. So these are again experimentations that you will have to do. You will have to try with a basic model, try with a baseline model, then you need to add more features, and you need to see how it becomes better at every epoch. Right, so this is again something that you need to do, and this is an example of a dropout that I added. Okay, you can uncomment it, you can run it, you can try it out. Okay, and you can see very clearly this is my architecture right now, and very clearly you can see that when I run this, I'm getting upwards of 91%, 92%. There's a scope to make it better, because very clearly if I train it for more epochs, I think it will improve to 93, which is phenomenally good compared to yesterday. Yesterday with Fashion-MNIST with a normal dense layer, ANN, normal neural network, we were getting only around 88%, 87, 88. But the moment I use CNN, I kept everything the same, but you can see the power of convolution layers, because we are able to retain the spatial information. We don't have to flatten the picture. And because we have not flattened the picture, the original information in the image is still retained. And these are the results we are getting for CFAR10. CFAR10 again, very similar. The only difference is I have not flattened the data. See the reshape 32, 32, 3. I did not have to flatten it and reshape it to 1D. I have retained the picture in the same two-dimensional, three-dimensional form that we originally had. So this is what we have here right now. And the rest of the parts are again very similar. And this is the part that you need to experiment, you need to try. I have just given a basic one with 4 convolution layers, but you can try it out. You can try to add, add some layers, remove some layers, and that is part of your practice. You see that, hey, if I reduce a convolution layer, what kind of results am I getting? Okay, so when I do this, the final layer you will have to flatten. And here I did go ahead and use some additional learning, because CFAR10 is harder. So we need some more, it's like, we need a little bit more power in my network to learn those final features, because these are colored images. So not like MNIST and Fashion-MNIST, they were easier, but here we need, we need some more power. So we are adding some extra dense layers, which is a good practice, with some dropouts so that we don't overfit also. So we are kind of, on one hand, we are adding additional power, by adding an extra layer, and on the other hand, we are compensating that by dropout. So this is also a very good combination. Instead of skipping the layer completely, a very good practice would be to add a dense layer and then compensate with some dropouts. So dropouts means that, okay, you are adding 128 neurons, and you're also parallelly adding a dropout to ensure that you are able to parallelly regularize the model so that it doesn't become too overfit. So you're not allowing all the 128 neurons to participate in the learning, but in every epoch, in every batch, you are only you're dropping 30% of the neurons, and only 70% of neurons are actually contributing in the learning. Okay, and when we go and train the network, we are able to get close to 75-76% accuracy. You can again use checkpoint callbacks. We can very clearly see there's an increasing pattern. So I only did it for 10 epochs, and we are seeing a fairly good improvement we are seeing. And the other very interesting thing you will observe is the amount of time. You can see 9 seconds. You try it with a CPU. If you don't use GPUs right now, you will easily get much more time it will take to run. Okay, so so once you until yesterday, until dense layers, it was fine. It was fine if you do not use GPU. But the moment you are using convolution layers, and you can experiment, you can try out. You can do it iteration 1 with GPU and iteration 2 without GPU. Just take the same code and try running it. You will see a phenomenal difference in performance. Okay, if you take CPUs, it might easily take more than 10 times, 100 times more than what you're getting right now. You'll have to wait for 3-4 minutes before you see one epoch complete. Here it is only 5 seconds, 10 seconds. There you will have to wait for, let's say, 5 minutes. You will see a noticeable difference, especially in CNN, because CNNs are very compute intensive. Okay. What I did in the rest of the notebook is something very interesting. I actually use transfer learning, and this is to demonstrate to you that you can theoretically take your accuracies up much higher. And we will see how it can be done. For the same data set, you can actually make it even better, and we'll see that. All right, now let's look at the next exercise. Next exercise is on flower classification. Let's see how we are applying the ideas of CNN once again for another very interesting use case on flower classification. So this is a little different from the exercises we talked about so far, because we are taking a real flower data set. And as we see the next phase of exercises, unlike taking inbuilt data set from Keras, what we will try to do in these exercises is we will actually work with some real pictures, right? Just to give you the flavor of what happens when we work with real pictures. So what I did is I already downloaded the data set. You can see this is my flowers data set. So we have total. So this is coming from TensorFlow. It's a default data set that is available in TensorFlow. I went to the link, I downloaded this, and I extracted the files. You can see. So we have 5 different classes of flowers: daisy, dandelion, roses, sunflower, and tulips. So we have total 5 different classes of flowers, and you can look at each and every folder, and you can see the flowers that are present in each and every folder. This is what real world computer vision will look like. You will typically have a set of pictures, or you will, let's say, have some folders with you, or you will click some pictures, you will organize them in the folders. And this is the general convention where you give the name of the class for each and every folder. So eventually we want to do classification, and we want to look at a flower and identify what is the exact um, class of the flower. That's what we want to do. Okay, and this is what. Okay, you can see this data set is a very old data set. That's why when you see date modified, it is showing 2016. So my system time is obviously much more than that's 2025 today. But this is a very old data set. This was published back in that time. That's why the folder was modified back at that time. Okay, you can see it's a fairly old data set. And the very interesting part about this data set is the variety, the sheer variety of examples that we have. So when we look at Daisy, see the different ways daisies can look like. So daisies can look like this, daisies can look like this. We have some close-up pictures of Daisy. We have some zoomed out images of Daisy. So daisies can be white, daisies can be yellow, daisies can be pink, daisies can be whitish pink. There's so many colors daisies can take, right? That's the incredible part. Like, look at this. There are so many ways daisies can look like. Daisies can also be blue, right? Look at it. So now and they can also be yellowish. They can be slightly reddish. And you can mix daisy with other kinds of flowers, and the model should still be able to pick up that it's a daisy. So the data collection part is very important. When you're doing these things in the real world, the variety of examples are phenomenal, right? So the more examples you have, the better the quality of your model. It will be harder to classify, definitely compared to the previous exercises. The flowers data set will be difficult to classify. It will be harder to look at each and every example of a flower and trying to classify what those flowers are, because the variety is phenomenal. Okay. Similarly, if you go to other folders, we can look at the rows folder. So initially, there's a lot of pre-processing you will have to do, and this is the default data set again available. But a lot of times you can see roses. Roses can be red, roses can be yellow, roses can be orange, roses can be pink. Okay, the roses can be white. So we are having close-up pictures of roses. We are having zoomed out pictures of roses. Look at this one. This is also apparently a rose. Somewhere there is a rose that the person is wearing, and the model has picked up, okay, there is some indication of a rose here. So data in the real world will be very difficult. It's not as if we have perfect pictures of flowers. So see how the model has to learn. It's pixels, right? So now we have lots and lots of input-output combinations. You're teaching a small kid that, hey, these are all examples of roses. Please learn from this. It is a very difficult problem, but we'll still try to build a network to do that. I wanted to also clarify, and these are real pictures. You will have some seeming, look at this one. This is also very interesting. This is actually a group photo, but when you maybe zoom in, you will start to see roses. So the model should pick up that, okay, these are also apparently white roses. It's very hard to make out, but that's exactly what I want to train my computer vision model to do. That, okay, pictures like this also are roses. So when you see a picture from a far away distance and you come across pixels that look somewhat like this, these are also roses. And this is very challenging. Why? Because there are some water droplets falling, and this will mess up the pixels, right? I mean, even if you try to zoom in, there's some small white spots that you will see because this is the water droplets, and it will mess up the pixels. These are all real world challenges of computer vision, right? So, and as I maintained right from the beginning, the baseline models are easy, but these are the kind of things that will actually take a lot of time. And also you will come across images which have nothing to do with a rose, right? Which have absolutely nothing to do with a rose. You want to say an example? I'll show you an example. Look at this one. Look at this one. It's a car. There is absolutely no indication of a rose anywhere here. So this is an outright wrong example that is given. So we have this picture in the rose folder, and it is like saying you're teaching the machine that, hey, you know what? Pictures like this are roses, which is not true. This is not a rose. By no indication is this a rose. I mean, if you try to use this data and train the model, it will learn incorrectly. This is not a rose. And a very, very important part of be it machine learning, be it deep learning, whatever you try to do going forward, you need to do this pre-processing, and you need to manually remove these kinds of images. So when you come across these kinds of pictures, you try to consciously delete and remove these kinds of images so that your training data does not have these kinds of pictures. So that it's like, you train machines the same way you train a small kid, right? Will you ever teach a kid that, hey, this is a rose? Imagine you go to kindergarten and you're teaching the kid about different types of flowers, right? You're showing, this is a rose, this is a rose, this is a rose. All of a sudden, you start teaching this is a rose. You will end up confusing the kid. The kid will not learn correctly. The same problem will happen in machine learning and deep learning also. So you should try to remove these kinds of examples. Now, with this in mind, let's move on. I will actually run this for you. To start with, I'll run this for you so that you actually get a feel for it, what's going on. Right? So initial part, let me run this for you. So first we will load the data. And this is my Colab VM. Make sure you are using GPUs. I told you how to enable it, change runtime type, and you to say T4 GPU. Okay. So we'll use the wget utility to go and download the data directly from the folder. And once you do it, on the left-hand side, you will see that the data will be downloaded. You see that data is downloaded here. Next, I will read the data set, and I will basically extract them out into the directories. Okay, so flower photos and all this. You need to refresh, and after a while, you can see that it will be extracted properly. It takes a while, but after you do it successfully, it will be refreshed. Okay, extract the pictures, please. And this is the part where you're effectively loading the data. Okay, you can see that now we have the data folder, and inside the data folder we have flower photos. Exactly the same kind of directory structure I created in my local machine. I'm now doing this in Colab. Okay, this is the initial part where you're organizing your data. Okay, just that you're doing the entire processing in the Colab VM. So we have daisy, we have dandelion, we have roses, we have sunflower, we have tulip. Same thing. You can expand daisy. You can look at the pictures. This is just like a virtual machine, right? You can double click on the picture. You can see the preview. This is how the pictures look like. This is the same thing that we discussed. Nothing is different here. You can see some of the sample images here as well. Maybe open up a couple and see JPG files. Okay. Now, so the first concept is that. Now, what are the couple of challenges that we have as we come to the solutioning. Couple of challenges. Challenge number one, all the images are of different sizes. When you look at real world data, friends, real world data, when we look at all these pictures of flowers in the folder, all these images will be of different sizes. So image one will be different, image two will be different, image three will be different. So the different images will be of different sizes. That is one thing to keep in mind. So different images will be of different sizes. Point number one. So you will have to resize your data. Point number two, you will have to convert these pictures into their pixel intensity values. In all the previous exercises that we did, there were 2-3 previous exercises we saw. CFAR 10, MNIST, Fashion-MNIST, CFAR 100. They were just for very academic exercises we did, but the data was already pre-processed. Everything was beautifully resized. Every picture was 28 cross 28, or in CFAR 10 it was 32 cross 32. Everything was beautifully done, right? We didn't have to do anything. So the resizing was already done. The pre-processing was already done. Everything was already converted to a array format. Everything was done for us. Here, nothing is done for us. So two very, very important things we will have to do when we work with real pictures. Point number one, we will have to resize the images. We will have to take each and every image, and we have to make sure that they are the same size, the same dimensions, A. And B, we have to make sure that each and every image, we have to make sure that we convert each and every image into its pixel values. So these are the two broad things that we will have to do. So please take care of this thing, okay? Please ensure that these two things you do correctly. And I will show you in my notebook how to do it. There are enough utilities in Keras that we can use to automatically perform that operation, right? So just to try it out, we are looking at some sample pictures. So we can see some sample images here, how some of the sample images look like. And we are specifically using the Keras load utility function. We're using something called load img in Keras, which can help us do this operation. So I will use something called Keras load image. And once I do that, you can see that every picture can be loaded. We can resize the pictures. This is the image size. You can clearly see the pictures. The sizes are different. This is what I meant to say. So this is 320 cross 260, whereas the image 2 is actually slightly different. It's slightly bigger. And this is how we resize the pictures. We're resizing everything to 128 cross 128. That's how we resize the images. Okay. And once you do it, it'll do like this. And second thick part is you are converting the images to a NumPy array for machine learning. So we're taking the same flower image. Remember, flower image was a picture, and we are using the Keras utility image to array function to convert the pictures into their corresponding NumPy arrays. Okay, you can use different utilities, and once you do that, remember, originally flower image was what? Originally flower image was this. If I run the code, flower image previously came like this. Now, if I run the code, this is flower array. We're taking the flower image and we are converting it to an array. So flower image is this, flower array will be this. See how we converted the picture into its array. Now this will automatically be done. 128 cross 128 cross 3. Why is it cross 3? Because remember, there are 3 channels. There is a red channel. We are looking at all the intensity values for the red channel. There is a green channel. We are looking at all the pixel intensity values for the green channel. And there is a blue channel. We are looking at all the pixel intensity values for the blue channel. So these are the different channels that we have right now. Okay, I hope everyone's aligned on this one. Okay, now moving on. So once the conversion is done, this is pretty much all that we have here. Now we'll read our training data and testing data. We are just parameterizing the whole thing. So we are using parameterizing 60 and 3. We're using batch generators to make sure we process our data in batches, right? Remember, I told you we should not process the data in one go. There are lots of pictures. I think there are 700 images per class. So if you look at it overall, there are 3,500 pictures, and each picture is fairly big, fairly reasonably big. Like we have got 1 MB per picture approximately. So if you have 3,500 pictures, it's 3.5 GB straight away you're utilizing in RAM. So the moment you're processing this entire data in one go, you are loading all the 3,500 pictures in RAM, and you're straight away going to be using up 3.5 this MB of RAM. So these are real challenges that you'll be facing when you're working with computer vision. So these are things that you need to keep in mind. Okay, yeah. So now let me go and run this, and you can define the generator model, and this is the part where we instantiate the CNN model. And this is the most important part, right? So this is how you can decide how you want to do it. So we're just keeping it simple. We're having only 2 convolution layers, right? So you can maybe add a third one. If you want to add some extra punch in the learning, you can add a third convolution layer. And this is 128, right? So this is always a good practice. Starts with smaller layers and then you increase the number of neurons, okay? So you start with 32. Con 32 means the first layer will learn 32 basic features, and then you build on top of that, you learn 64 advanced features, and then you build on top of that, you learn 128 more advanced features. So that's the way how we generally go ahead and do it. And also as a best practice, we try to add some max pools, right? So you do convolutions and then you do max pools. This is also a good practice. So max pooling is a way to kind of reduce the number of pixels. Okay, so we can add a little bit more weight. Maybe we can start with 16 and then 32. I'm trying to maybe increase the layers a little. So this is 64 and this is 128. So we have made it fairly big, fairly big. So I've added 2 more convolution layers. I've added a max pool layer. Then we do flatten. Then we add an additional dense layer for some additional learning. And this is the dropout you can see. We're adding a dropout so that it doesn't overfit. Okay, so these are some of the core ideas that we've implemented. It's always a good practice to do batch now. I'm not doing all that right now because otherwise it will take a lot of computation time. So I'm skipping those parts, but this is the baseline model that we have created. Rest of the parts are similar. We have accuracy, categorical cross entropy. Why? Because we are having a multi-class classification, and this is what your Keras summary will look like. See how simple Keras makes it to go from concept ideation to implementation. This is one of the best things about the Keras framework. When it was initially, it made deep learning easy. It made deep learning very easy. You don't need to spend and waste a lot of time thinking about variables and from a programming concept. So now you can focus on the problem statement. What is it that we are trying to solve? We need this much inputs, this much outputs. So Keras makes it very easy to go from ideation to implementation. So this is the architecture we can see, and now we can train the model. We are setting a batch size of 64. We'll go in 64 batches of 64 and we will train the model. I think we can increase it a little. We don't need to take 64. We can increase it. Maybe I'm just thinking 256 will be 256. And we can actually increase it because the pictures are fairly small. I don't think we have very big pictures, so they're fairly small. So we can afford to increase it because if you take more batches, then you're actually using GPUs more efficiently. Otherwise, the training will be very slow. So if you take more pictures in a batch, that means you're parallelly processing all of them. So you want to really take advantage of the GPU parallelism feature as well. So if you take a very small batch size, it will take a long time to process. So let me run this for you. And we can use train generators to do this. Let me run this for you. So model.fit, it will take a fair bit of time, but you will see that you will see the progress. You will see the progress. Okay, everybody take a look at it. So the compute will go up. You will see gradually the RAM utilization will increase because we are loading the pictures in the memory. Okay, you can see this one in action. Okay. We're starting off very small. We're starting off in a basic way. Training accuracy 22%, testing is 15%. So this is fairly basic, and we will see how the network becomes better. So yeah, so it's a very gradual learning that is happening. You can see. Okay, it's a very gradual learning that is happening. Epoch number 4, the training has increased, the testing has increased. So this is a good sign. This makes me very confident. Yes, the training is going well. We need to monitor. Maybe assign this to a history object and then plot it. All that we should do. So the training continues to increase. The validation kind of seems to stagnate. This is where the problem seems to occur. Can you see? I can train it for a few more epochs, and if I continue doing this, yeah, validation is showing some sign of increase, but beyond the point, it will not increase. Maybe I can take it up to 30. I can take it up to 20 epochs now, and increase my batch size a little because let me see, the RAM is still there, right? Yes, I think we can afford to take a higher batch size, 1024. So and you can actually make these changes, right? So these are runtime changes. See, I mean, so the point where you ran the model for 10 epochs, you would have got some weights and biases, right? So when you make these runtime changes, now those same architecture, the same weights will be carried forward, and you can train it further for 20 more epochs. So you don't need to run and initialize right from the beginning and do it. You can straight away make these changes here, and you can say epochs equal to 20, and from the last part, it will be executed. It won't be executed from the beginning again. So whatever W's and B's you had, I think the last accuracy we got was close to I think that was close to 50%. So it will start from there. It will start from those weights and biases and other kinds of things you can add. You can add checkpoint callbacks and all that. Okay, the only difference is, see what happened here. When I take 1024, I'm utilizing the GPU. See, I'm getting 16 GB of GPU, right? So why not use it? I'm doubling the GPU usage. So if you take a bigger one, maybe if you take 2048, you will double the GPU usage. So that may not be feasible, but you'll try to consciously take a higher batch size so that you're utilizing the the parallelism feature. Okay, that's the important part. Okay, so these are all fine tuning things that you will do, and I think this comes with more and more practice. But just wanted to share a few things with you so that you get some idea, all of you. So epoch 1, it's taking substantially more time now. You can see. Let's see. I mean, we can see the training accuracy will continue improving. The training accuracy will continue becoming higher, but the testing after a point will stagnate. After a point, the testing accuracy will start to stagnate. So I will let it run for a while because this will take a little time. I think this will take a while to train. And then what I wanted to show you was the aspect of what happens when I do augmentation. Or you know what? Let me stop this because this is taking a lot of time because I think I added a lot of layers. That's the problem. So let me go back to how it was before. Yeah, because I added a lot of layers. That's the biggest culprit. Let me keep it simple. Let me keep it simple, 3264, because those extra convolution layers are really eating up time. Okay, that's the problem. Let me not keep it. Let me keep it simple how it was. Other things are fine. Batch size is okay. Let me keep it to this. This is okay, and let me train it for 10 epochs. Okay, let's do this. Yeah, because we added so many convolution layers that was really messing up the whole thing. And now we can again start from the beginning. No need to load the data. The data is already there. No need to do this. So you just need to kind of start from the part where you initialize the model. Okay, so you can start from here. Generators are all okay. This is the part you start from here. Okay, reinitialize the model, and then you can retrain the thing from scratch. Okay, so let's do this. This will be significantly faster because obviously there are very few convolution layers, and we've reduced the number of layers by like 50% now. This should be significantly faster comparatively. So let us see. But because we are using shared resources, no, you'll find some bottlenecks will happen. Some bottlenecks might be there somewhere. It might get stuck. So if you come across those kinds of problems, which are very normal, because you have to remember Google is giving this to you for free. You can go to this thing called runtime. The same options that we had before. So you go to runtime and you can say restart session. Okay. Sometimes you will also have to disconnect and delete runtime. So this is where you see that the system is hanging. So they're very common, like especially with GPUs and all. Very common to see the system will hang at times because it's a shared resource. Okay, you might come across these kinds of bottlenecks. So you can disconnect and delete the runtime, and you can run again because we cannot complain. We're getting it for free, right? So these are very common issues that you will see in collab, especially with GPUs, because GPUs is where this is a very costly resource you're trying to access. So I will keep it on. I'll keep it on for a while, and let's see. And you will actually observe the concept I wanted to clarify here is you'll observe that the network will significantly overfit. The network that you end up getting will significantly overfit. And how do we prevent that? What is the solution for overfitting? First of all, why is it overfitting? It will overfit because we have got uh, we've got less number of images, right? Only 700 pictures per class is not a lot of pictures. We've got different varieties of images, and we have only got 700 pictures per class. That's the issue. Only 700 pictures per class is what we have. So the number of images are comparatively very less. That's what we have here. It's a good idea to now do image augmentation. And augmentation is the process where we take a picture. And so when we have very less number of images and we try to build a very complex model, because CNN is a complex model. CNN is where you're trying to extract the features from the pictures and you're trying to classify accurately. So it is like on a very small data set, you are trying to use a very complex model. And that is why it is overfitting. There's a tendency of overfitting that you will see that will play out here. On a very small data set, you are trying to use a very complex model. You are trying to build a very deep network, a deep architecture, a very complex model you're building on a very small data set. That is the issue that you will find here right now. And that's why you are getting overfitting. How do you resolve that? You will do augmentation. Augmentation is the process where you take a picture and you try to generate different variants of it. For example, you have the original image and see how we flipped it. See how we shift the picture, how we zoom the picture, how we transform the picture in different ways. So the idea here is that this is the original image, right? This is the picture of a dandelion flower. The left hand side is what you would have labeled. The left hand side flower is what you would have originally labeled. And from that left hand side image, we are generating many different variants of the right hand side images. That's the idea. So the left hand side image is what you originally had. This was the picture of the flower you originally had, right? This was a labeled image of the flower you originally had. And from that labeled image of the flower that you originally had, you are trying to create many variations of the picture. You're not trying to create a new image from scratch. You are simply taking whatever picture you originally had and you are trying to create different variations of the image by zooming it, by shifting it, by shearing it, by shifting the picture. And all of a sudden, you would have managed to create different variations of the picture. So initially, we started off with only 700 images per class, right? Approximately. Every type of flower, we had only 700 varieties of it. Now, all of a sudden, by applying these transformations, we will be able to get close to, let's say, 5,000 pictures per class. So this is a very nice way how we are able to generate pictures, generate data. Very common way how we generate data. And once we do that, once we train the network, because it's a bit of a bottleneck, I think we stuck here. So I'll try to restart and disconnect the runtime in a minute. So again, whenever you strike these bottlenecks, very common. Good that we got it because I wanted to show you. See, it's stuck. The training seems to be stuck because some resource bottleneck happened because I made some changes. I did some things, if you remember. So whenever you come across these things, don't wait. Just go to runtime and restart session, or disconnect and delete runtime. Take a new machine, take a new VM, and try it out from the beginning. Okay. So now when I do the augmentation, when I rebuild the model, you will see that the overfitting part would have gone away. It is still not a very good model, but the overfitting part has substantially reduced. We are not getting overfitting anymore. Why? Because the training accuracy and the testing accuracy is very low. So the image augmentation is a very standard part of what you will do in general computer vision tasks. You take the original picture and you transform the picture in different ways to generate different variants of the picture. So that is what we refer to as augmentation. And the final piece of the puzzle is what we refer to as transfer learning. And this is a really incredible technique. And by using something called transfer learning, we are able to get a model which is giving 93% accuracy. Look at this, 93.89%. So we started with something like 50, then we went to something like 70, and with transfer learning, we are touching close to 93. This is magical, right? So what is transfer learning? See, so far what we have done is we have just built the architectures from scratch. So we have some data, we designed the architecture from scratch by hand. So you are taking a call. You are saying, okay, I want to have 2 convolution layers, 32 filters, and all that. So we are trying to do all that from scratch. So you are adding 5 layers, and each layer has 10 filters, 15 filters. How many dense layers you want? All with transfer learning, what we do is we are now going to take the advantage of pre-trained models which are already available. So we will not be creating these models from scratch. We will use models which are already available. There are certain models which are already available. So we will use those models, we will use those architectures. We will use whatever weights and biases are already, like those models have already been trained up to a certain extent. So whatever weights and biases, W's and V's are there, we will use all of that. And based on that, we will go ahead and build the models. And that's the core idea of what we are trying to do in transfer learning. It's a magical technique. It's a very powerful approach where you take the same model, and the core idea of transfer learning would be you take the same model and you go ahead and you try to use a pre-trained model for your tasks. You try to use a pre-trained model for your specific tasks. That's what we do in transfer learning. If I have to give you a simple analogy of transfer learning would be how we learn. How do we learn something? We are also doing transfer learning all the time, right? So let's say if I ask you to solve a problem, if I ask you to solve a problem, you will not be solving that problem from scratch. So chances are very high that you will not be solving that problem from scratch. We are also by default doing transfer learning all the time. So when given a problem, you will look at what you already know from before. If you have solved a similar problem before, you will look at your data, you will see what kind of problems you have solved before, whether you have solved a similar problem before. You will look at that and you will utilize your learnings from your previous task in your new task. That is the idea of transfer learning. So given a new scenario, one looks to reuse his or her knowledge. You don't do it from scratch. We don't try to define the layers from scratch, but let us go and see what is available. Let us use some models that have already been trained on similar data. Let's say if we are trying to do flower classification, can I see in my repository whether we have other similar models which have already been trained on flowers? So that means we would have learned the weights and biases, right? If we have other similar models which have already been trained on the flowers data, we would have already learned the weights and biases. So let me use that. For example, if you want to learn how to play tennis, you don't have to learn everything from scratch. You don't have to, like, even simple things like tennis involves a lot of skills. You need to have good hand-eye coordination. You need to be able to run around the court. Like a lot of things, right? A lot of skills that we humans we take for granted. Skills that we have learned over a long period of time. You can't just go to a tennis court and figure out how to see a ball and guess its speed. So these are things the human brain uh, absorbs at a very early age. Concepts of speed, concepts of motion, predicting where the ball will be so that you can take the bat right at that position and hit the ball. These are incredible skills, and this you cannot learn in from scratch, right? So let us use those skills I already have from before, which I've acquired in my life, and let me use that to solve the problem. Applying knowledge on new tasks which I gained earlier, that is called transfer learning. And this is the philosophy that even machine learning we will apply, especially in deep learning. Why? Because training something from scratch takes a lot of time. This is one of the biggest problems, right? See, I mean, we are already getting a bottleneck. That's what I was talking about. We're getting a bottleneck already. So training something from scratch will take a tremendous amount of time. So it's not practical. There are a lot of practical limitations also, right? So when you try to train something from scratch, it will take a lot of time. If you try to define your network, if you try to define your convolution layers, how many filters, like the way we did the exercises so far, it will take a tremendous amount of time. And if you don't do that, then you will have to take a lot of data, right? Otherwise, it will overfit. We saw that already. Getting the data is very expensive, right? In these exercises, I'm simply giving you a folder and I'm telling you, hey, this is a daisy, this is a dandelion. But somebody had to do this work, right? Think about it. Data annotation and data labeling is something that had to be manually done first. I mean, if you're working on a real world project from scratch, you will not have this data given to you in a platter. Maybe some other team would have collected. There's a cost involved. There's a certain amount of time somebody would have spent. There's money that would have been invested to get the data labeling done. And only then the end result is you have that folder. You have that beautiful folders and subfolders where the pictures are there, the classes are labeled. But that will take time. It's expensive. And they require a lot of data, right? And that is why transfer learning is so useful. So transfer learning is like taking a shortcut. If I already have something from before I use it, that's a simple idea. Simple concept of transfer learning. And how will we do it? How will we do it in practice? In practice, this is the way how we will implement transfer learning. So let's say you already have a architecture that you defined from before. You will go and simply, so what you will do is you will go and uh, this is what happens basically, right? So whenever we do computer vision, we talked about it that the initial convolution layers, we always extract the most basic features, right? Initial convolution layers, we are always learning the most basic features, low level features, basic shapes, basic color patches and all that. Next convolution layers, you're building on the initial layers and you're learning more advanced features. And the final convolution layers are typically learning high level features, features which are very specific to the task at hand. Right? If you're trying to do flower classification, you will actually see entire shapes of flowers playing out. So when you're doing transfer learning technically, this is the way how you will do it. You will already have a model. You will typically remove that top layer because the previous model was meant to do something else, right? So you will remove that top layer and you will use your own dense layer for classification. Because your task involves classifying, let's say, 20 probabilities. Or in my case, we have the flowers classification. We need to predict 5 classes. So we need to do dense of 5. So the other model would, let's say, was predicting 10 probabilities or 15 or 100 probabilities, whatever. We don't need that, right? We don't need the dense layer. So take the convolution layers because the convolution layers are basically where the features are learned. So use those layers, use that pre-trained model, freeze those layers, and add your own dense layer. This is the way how we'll do it typically. And if you think about the implementation, this is the way we will do the implementation. This is exactly what we will do in the code now. We will take the same flowers data. We will use a ResNet model with frozen layers. ResNet is like a pre-trained model. There are many such. You can Google out. There are many such other pre-trained models that we have based on the ImageNet dataset. We are just using one sample, one called ResNet. And whatever features, remember I told you that convolution layers, what are they doing primarily? They are feature extractors. So once you are able to successfully extract the features from the image, now you will add your own dense layers for the additional learning. So dense of 5, activation softmax. That's the way how we go about it. Just to further pictorially describe this to you, this is actually what's going on behind the scenes. You can see, very interesting. You can see a simple example of CNNs in action. On the top one, you have pictures of people's faces. Let me show you with a bigger slide. So let me show you, get a better idea of what's going on. So on the top part, you see images of people's faces. So when you pass it through the convolution layer, the first convolution layers are the same for both. Can you see? So whether we have persons' faces or whether we have images of cars, the initial layers look the same. The first convolution layer or the initial convolution layers, the low-level features are kind of similar. You see diagonals, color patches, you see 45 degrees, 60 degrees. So you're trying to find edges, you're trying to find horizontal lines, and those will be very similar across any kind of image, right? If you try to zoom into a picture enough, you will start to see edges in the picture. This is very evident. But as you go deeper into the next layer, when you go to the mid-level features, the mid-level features will start to vary. So here you can see, parts of the face, like the eye, the nose. Here you will see parts of the car, the tire, the chassis, the bonnet, and all that. And as you go to the top layer, the output layer, the highest high level features, the high level features will be completely different. Here you will see, we are getting entire pictures of the person's face. So this is the hierarchy of features that I was talking about. In yesterday, we saw an example, and today we saw some further ideas of, and this is what transfer learning leverages. This is exactly what we will leverage even in transfer learning. So when we use a pre-trained model, the pre-trained model will usually do very well in the initial layers. So we can use a model that was trained on some other task. Let's say here we can use the model that was trained on the car data. And we can use it for the face recognition. How? Because the initial layers will remain the same. So when we use it in the code, we will typically freeze the initial layers because whatever initial features were learned, they will remain the same across both any problem domain, right? But then we can now fine tune the top layers. We can fine tune the top layers with respect to our problem. So these are some of the ways how we can use this concept. And how are we doing this in the code? It's very easy actually. The code is very simple. In the code, we are simply going and first we are adding, we are loading the ResNet model. So you can see incorporating transfer learning. So first we load the ResNet model. This is the ResNet 50. This is all part of Keras, TF Keras applications ResNet 50. So step number 1 is we load the ResNet model. Step number 2, we say include top equal to false. We are specifically not including the dense layer because ResNet was meant for a completely different task. ResNet was meant for a completely different task where it was classifying other classes, right? We don't need that. We just want to know the features of the model. That's it. And then we will reuse it for our own task. So we will not use that top layer. We will not use that dense layer originally, which was part of ResNet. So we will exclude that. So when I load the model, you can see the summary. So it is taking a 224, 224, 3 picture, and this is a huge model. Look at it, massive convolution, 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 huge. This is simply, we will use it as it is. It's a fully pre-trained model, and at the end of it, we will end up getting this many number of features, 7 cross 7 cross 2048. So we take the picture, we pass it through all these pre-trained features, we get this output, and now on top of that, we will add our intermediate layers. And this is the pre-training part. This is the freeze part that I was talking about. You can either opt to freeze all the layers. We can say for layer in model.layers, you can set all of it to false, or you can basically retrain some of the ending layers. You can flatten, you can add your own dense layer, dense of 5 activation softmax, and you can look at the final model summary. Okay, so this is your input image, 224, 224, 3. You're passing it through all these pre-trained layers. So you're loading two things. One, you're taking the architecture, and second, you're taking the weights. And then you can fine tune that. And at the end result will be dense of 5. Here we have added the dense layer, remember, dense of 5. And now we can train the model, and we're getting a phenomenal accuracy. And why is it happening? Because we are able to reuse the weights of what was already learned before. We are not starting from scratch. We're not starting from scratch, because if we start from scratch, we need to go for more epochs. We need to tune a lot of hyperparameters, learning rate, all of those kinds of things we have to do. Now, transfer learning is helping us take a shortcut. This is like a shortcut. If it's like if you already did something, no point in reinventing the wheel. Let's use that. Let's use this architecture. Let's use whatever weights we had, and let's use that to solve the problem. So that's the magic of transfer learning. That's the idea. As I was saying, I think this runtime is taking a lot of time. So I think I'll disconnect the runtime and let me delete it. And so when you delete the runtime, what happens is everything goes away. It will reconnect to a different machine. So it's allocating a runtime, and it will give me a new VM. Right? So I'm deleting the runtime, and what will happen here is you need to again run from scratch. Yeah, because this is a typical, very common thing. Good that we saw this in the class, so that next time anybody sees a similar issue, you know what to do. Okay. So don't be confused. It's very normal to come up with these kinds of bottlenecks, because remember, it's a free compute engine that Google is giving you. I think it's taking time to even allocate a new VM. Maybe there's some resource constraints right now. Connect to a hosted runtime. Let's see. And it will take some time to allocate the new VM for me. Okay. So transfer learning will be useful in a lot of different domain areas. So transfer learning will be applicable in a lot of different domain areas, not only in the context of computer vision, whatever we are discussing right now, but transfer learning will be a very, very key concept even across other kinds of domain areas as well. Okay, so please keep this at the back of your mind. Uh, so transfer learning will be very, very relevant even for images, audio, video, text. So it's a very, very common idea. Okay, so yes, so the concept here is that you will not be building your models from scratch. Okay, you do not have to build your models from scratch. And in transfer learning, what you will do is you will simply use a pre-trained model, whatever was trained before on a different task, use that for your current task. And what you will use particularly, you will use the initial layers of the convolution uh, neural network as it is. So the initial conv layers can be reused, and the final ending conv layers will be basically fine-tuned and retrained. So that's the way how you will work towards it. So the initial convolution layers you will explicitly go and the initial convolution layers you will go and reuse, and the ending convolution layers you will effectively retrain. You'll fine tune specifically for your task. And that's the way transfer learning plays out. And there are a lot of different models you can explore. In fact, in the same notebook, if you go and look up TF Keras applications, you will see a lot of other different types of architectures. Like you will see something called VGGNet, you will see ResNet, you will see InceptionNet, EfficientNet, okay, DenseNet, okay, AlexNet, ZFNet, GoogleNet. There are a lot of different types of nets you will find. So many pre-trained models you will find, and it's not only with respect to Keras. You can also go to other repositories like Hugging Face. There are a lot of other communities that are there, like where people or the communities have already taken some data and they have built some model, and you can just go and reuse those models. So a lot of those kinds of things you will also find. I had this beautiful diagram that I showed you before. This is a wonderful way you can train a neural network, and you can actually visualize the entire neural network training. So this is just something I wanted to mention very briefly. how you can effectively visualize this neural network training, and you can kind of just pictorially use all the different parameters that we talked about and go about it. Okay, so let's say you can start off with 0 hidden layers as an example. Okay, it's a good way to actually see and understand exactly what is going on behind the scenes. So if you just take this one, if you don't use any hidden layers, you will clearly see that the training and testing losses remain high. This is expected, right? Because if I do not take any hidden layers, you can clearly see my training and testing losses are high because we are not able to train the model. So because very clearly we cannot do a linear separation between the classes. Okay, it's a non-linear model. So we will take a single hidden layer with 2 neurons, and if you do this, you will get an incrementally better model. See what happens. The 2 neurons basically means that the first neuron is learning this decision boundary, and the second neuron is learning this. If you hover over it, you will get a very good understanding what's going on. You will see. You will see the first neuron is learning this decision boundary, and the second neuron is learning this decision boundary. So very clearly, 2 is not enough. So maybe if I need to take it to 3. This is what I meant, like establish a baseline, start simple, and then make it complex. Don't start with something complex, because if you start with something complex, then it will be very hard to compare. You always start small and then you grow. This is a general philosophy that we follow in deep learning. And if you go and now take if you now take another neuron, you don't need to add a layer. Just take another neuron, and now you start the training. Look at this. It will take a while. It might take a while, but eventually it will figure out. Look at this. Look at this. It takes a few more epochs, but within a single hidden layer and using just 3 neurons, we're able to build a model. Okay. Maybe if I add an extra neuron, we can check. We can now compare. This is the comparative analysis we will do. That by adding an extra layer, what are we getting? Maybe you might want to, instead of saying dense of 4, I told you this already. Maybe take smaller neurons in each layer. Maybe add another extra layer. And maybe with this now you can compare what you're getting. If you add an extra layer, what kind of patterns you're actually getting. Okay, so you can do this one, and you can check. Okay, and and you can see that network is actually forming beautiful. I think it looks a lot better this time, right? And this is the trade-off, right? So after a while, after some training, you will see that it's very beautifully converges to maybe 0 training loss and 0 test loss. Okay, you can start to see. But what I meant to tell you is that you don't need 6 layers. You do not need 8 neurons per layer for this problem. We are able to solve this problem just using 2 hidden layers, or even a single hidden layer, but you don't need 6 layers, right? Even if you do it, no problem, you'll still be able to solve it, right? See, I mean, you can still solve the problem. It's not that you cannot solve it. You'll still get to a close to a 0 loss. It'll still happen, but I mean, you don't need it. You don't need such a powerful network to get the job done. Okay, so this gives you a very nice visual way of comparing what's going on. It's just learning rates and all you can compare. Okay, yeah. So I think this is still kind of stuck. So what I will do is, yeah, I mean, this is maybe reduce the batch size a little, because I remember I took a very, very high batch size, and this I think is the bottleneck. This is the problem area. So we'll just try to take a smaller batch size and run this once again. Let me restart the session and let me do this. Okay, yes. So there it is. I will just go and run this for you, because I wanted to show you the overfitting part. I mean, obviously you can run it at your end also, but I just wanted to show you the overfitting part, how it's playing out. So take a smaller batch size, because the problem is that it's trying to, all these pictures are trying to get loaded together. And I think my hunch is somehow the GPU is not able to, make way for it. That's the issue. So we'll try to reduce the batch size, and we'll try to retrain the model. You'll get some intuition on these things as you practice more, as you learn more, as you get some experience. But I think that's the reason, that's the problem that we are facing. It's not always that the resources are constrained, but now I think you can see that the training has picked up. So we are able to now accumulate that entire batch in my capacity. Okay, yeah. So it will not give you any obvious errors, but like I think, as I said, like with experience, you try to figure out these things over time. Like what the issue is. Sometimes it can be resource constraint, which it was in this case. Now we know why the resource was constrained, because we were trying to load too many pictures in the batch. So we were constraining the capacity in a big way. So you can see that after training for 10 epochs, let me show you what's going to happen. This is the initial part, right? Initial part, what I was explaining. Very, very basic CNN model we are trying to build without augmentation. And you will see that the network will overfit. After a while, I mean, initially you can see the first 5 epochs, everything seems to be good. The training score is going up, the testing score is going up, everything seems to be good. But after a while, you can see that especially from the fifth epoch onwards, the training score seems to be increasing, but the validation score seems to be stagnant. This is the pattern that we will see. Can you see the training has gone up from 64 to 72, 72 to 78, 78 to 83, and the validation is stagnant at 60. So we are already starting to see overfitting at around this epoch. So this is what I wanted to basically demonstrate to you, that when you do not do augmentation, these are the kind of real world challenges you will face. Okay, and why is it happening? Because remember, we have a very less number of images, and we have a CNN model, which is a fairly powerful architecture, and it's trying to learn all the patterns perfectly. It's trying to do very well on the training data, but it's failing miserably on the testing data. And then we use augmentation and transfer learning to resolve the problem. So the next part of the discussion, what we will do is we will get into a couple of exercises, just a few exercises we will do, and we will also enter into the beautiful world of advanced computer vision. So far we have just discussed about classification. You look at a picture and how you uh, predict what is the object in the what is the class of the picture. Is it a is it a daisy? Is it a dandelion? This is what we did. And now we'll enter into some more advanced computer vision problems. What else we can do with images? And obviously text. So we will also get into RNNs and recurrent neural networks, give you the idea what RNNs actually are. So that is the next part of our discussion that will follow. Okay, and we'll start from there now. So let's start on with the conversation on computer vision. So far we have discussed about image classification. All this while we spent in the last session, we talked about how do we do image classification, given a picture, how we pass it through the convolution layers. And we also talked about transfer learning, where instead of building the architecture ourselves, instead of trying to figure out how many convol layers we want, how many filters we want, we can straight away use a pre-trained model. Okay, so we were able to use something called a ResNet pre-trained model to achieve our to perform our tasks, right? So we don't have to go and do anything from scratch. If we want to achieve something, we can use a pre-trained model, and by using a pre-trained model, we were able to achieve like our objectives. Okay, so the pre-trained model was already trained on some past data. There was some data that the model was already trained on, and we were able to use that model on a new task. That's the whole idea of how we used the uh, transfer learning approach. Now, what other kinds of problems can be solved? Apart from classification, if you look at the whole domain of computer vision images, what other kinds of things can we do? So far, what we did was this. We looked at a picture and we used a convolutional neural network to predict what is the class in the picture. Is it a cat? Is it a dog? Is it a car? What is it? That is where we used a dense layer and all that we discussed. Now, what we are trying to do here is we are trying to additionally understand where is the object in the picture. So apart from the what, we are also trying to figure out the where. That's what we are trying to do. So apart from the what in the picture, we are also trying to figure out the where in the picture. So we are looking at the image and we are also trying to question the where part. What are some of the applications? So a very, very popular one is face detection. We have all our smartphones, and next time you take a selfie or you take a group photo, you would have seen that when you click up a photo, when you click an image, automatically the faces in the image are automatically highlighted. So the faces in the image are automatically highlighted. So a bounding box or a rectangular bounding box is automatically formed around the face of the person. Right? That is a good application. So not only are we trying to figure out the who, that what is the image, what is it, a person, is it a car, whatever, but we are also trying to find the placement. That is a very, very popular application of computer vision. And there are a lot of other use cases. A very, very popular use case is if you look at the roads where traffic cameras are used to monitor road violations, and they are doing object detection. So you try to first find the car, or first you try to find the vehicle. And from the vehicle, you try to find out the number plate of the vehicle. So there are two things you're trying to do. First is you're trying to find the vehicle, and second is you're trying to pinpoint on the number plate of the vehicle. What is the number plate of the vehicle under consideration? And from that, you're trying to do OCR and you're trying to read the different characters in the number plate. And then you, like whoever is the linked person or whatever is the linked mobile number for that person, you send a text message and for the specific road violation. So that's the way how we uh, conceptually go about this whole process. Okay, these are some applications of object detection. Now, how do we do this? How do we actually do object detection? How do we do this? What is the concept? The concept is this. So until now, we are sorted. This is something we know. We take a picture, we pass it through the convolution layers. This can be a pre-trained model also, right? And we get the features of the image. We talked about this part. And when we extract features, we know that the initial layers, we extract basic features, more advanced features like that. They're like hidden layers, right? Now, in detection, what we are additionally doing is, again, you take the picture, you pass the picture through the convolution layers. The convolution layers are used to extract the features of the image. You look at the picture and you try to figure out what are its features. You extract the features of the image. That's the first part. And once you get the image features, now there are two simultaneous networks you build. In one part, you are trying to do classification. You try to identify what is the object in the picture. And in the second network, you try to do object detection. You try to find out the bounding box coordinates. This is like a regression model where you try to predict what is the X, Y, W, H. So if I go back to the original image and try to demonstrate this to all of you. So all that we are doing is we are looking at the image and trying to find out what is the class of the picture. This is the original picture, right? You're passing it through the neural network. And the first thing that you're doing is you're trying to identify uh, the first thing that you're trying to do is you are trying to identify what is the class of the image. So given this picture, you're passing it through the convolution layers and you are trying to figure out what is the class, what is the image class. And the second thing you're trying to figure out is the bounding boxes. You start from somewhere here, and this is your x, y. These are the starting coordinates of your bounding box. This is your x, y, x comma y. And then you find out what is the width of the rectangle and what is the height of the rectangle. So this is the width of the rectangle, W, and this is the height of the rectangle, H. These are the four additional numbers that you're trying to figure out. Until classification, we are sorted. We already discussed this, given a picture, how we can classify. We already know how to do this, right? So additionally, based on the image features, you're also trying to find out the four numbers that correspond to the bounding box. This is the additional part that we are trying to do in detection. And there are different ways we can do it. We'll come to those conversations. What are the different ways how it can be done? But this is broadly what we are trying to do in a detection model. All right. So continuing on with the conversation, we have the image and we are trying to identify, as I was mentioning before the interruption, we are trying to figure out what is the uh, class in the picture and what are the bounding box coordinates in the picture. So there are two things that we are trying to do in a detection model. We are taking the picture, we are passing it through the convolution layers because we have to extract the features of the image, and this can be done through transfer learning. We don't have to build something from scratch. We can absolutely leverage transfer learning. And based on that, we can A, find out the class probabilities, what is the object, and B, we can find out the bounding box coordinates. We can figure out where is the object in the picture. So both the things we can ask, right? Now, conceptually, how do you do this? How do you train this kind of a neural network? So when you talk about object detection, what are we doing? How do we train this kind of a network in practice? So what we can do is we will have total two types of losses, right? The classification part of the network will have something called the cross entropy loss. This is something we have been doing all this while. We know how to train a neural network. So the classification part of my model will have a categorical cross entropy or a binary cross entropy loss. And the regression part of my network will have an MSE loss. Something we did in our very first case study on Boston housing yesterday, if you recall. Okay, so we have two networks. Classification will have cross entropy loss, and regression part of the network will have MSE MAE loss. Now, understand one thing conceptually. Whenever you're trying to train a neural network, whenever you're doing gradient descent and you're going about the process, you cannot have two separate loss functions, because the entire concept that we have studied, we cannot have two different loss functions. We need to have a single loss function that will kind of perform both these things. So now the objective would be how we can have two different loss functions like what you have here, and how do we go and convert the whole thing into a single loss function. That's the objective that we will try to accomplish here. So how we will have two separate loss functions. So we have a separate loss function for classification. There's a cross entropy loss that we have for classification. We have a MSE or MAE loss that we have for regression. So how do we take the two different loss functions that we have right now, and how do we combine it into a single loss function? Because when you do gradient descent, remember, the foundations of gradient descent remain the same. We are trying to find out the weights and biases. We are trying to fine tune the weights and biases in our network so that we are able to minimize the loss. So that is the foundation of gradient descent. That remains the same. No matter what kind of problem you're solving, the foundational ideas of gradient descent remain exactly the same. And that is what we are trying to do in gradient descent fundamentally. So we try to find out what is the optimal value of weight, what is the optimal value of bias B, such that the overall loss is minimized, the loss L is minimized. So we need to have a single loss. We cannot have two losses. So what do we do in this network? We try to figure out a way to combine these two losses into a single loss function. That is what we try to do. And you can see this is the way how we calculate the single loss. So we take some weighted summation. So we have a classifier loss function, which is cross entropy. We have a regressor loss function, which is MSE, and we try to do some kind of a weighted summation. So I'm getting a little technical. This is the architectural aspects, which honestly are not relevant for this training, but I'm just trying to give you a very, very broad overview as to how detection models inherently get built. But there are lots of different ways of doing it. There are lots of different architectures that are out there. These are basically region-based CNN models, but this is the big picture idea. There are two separate parallel networks. There's one network that is used to, work on the classification part, and there is one network that is trying to work on the regression part to find out those bounding box coordinates. And we try to figure out some way to combine those two losses and get a total loss. This is the weighted summation that we do. Another very interesting observation here is, you might be asking this question that why is it that we have a higher weightage for classification? You can see very clearly in the diagram that I'm showing, I have a slightly higher weightage for the classifier loss, and I have a slightly lower weightage for the regressor loss. So what is the intuitive reason why the classifier loss is slightly higher than the regressor loss? The intuitive reason is because the classification part of my network is kind of more important. So what is the reason why the loss is higher, the weightage is higher for the classification component? Because the classification part of my network is considered more important. So imagine you look at a particular picture and you try to classify what is the object in the picture. So the classification part is more important, right? Think about it. Like if you see an elephant, it has to be classified correctly as an elephant. You cannot call it a dog or you cannot call it a cat. That is very important. The regressor part, even if it is a little erroneous, I think it's okay. We can still discount it, we can forgive it and all that. But the classifier has to be correct. If it's actually an elephant, but you call it a lion, and if it's actually an elephant and you call it something else, then it's a problem. Then it's a problem. You cannot, I mean, there are no compromises allowed there. The classification part has to be correctly done. But the regression part, even if the regression part is a little bit off or the regression part is little erroneous, it's fine. It's fine. So talking about the regression part, if you see a scenario where the predicted bounding box is something, but the actual box, the actual rectangle where you locate the object is something a little bit different, it's fine. So that is the intuition why and how these weightages are arrived at. And finally, how do we measure the model's performance? So there are three key ideas we covered. One was it is a kind of a non-sequential model. There are two separate networks we talked about. One is a classification network and a regression network. Second key idea is the loss. There are two losses, and we have to find out a weighted manner to combine the losses, giving a higher weightage to classification. And the third key idea is how do we measure the performance of the model? How do we measure the accurate performance? Because all this while we were working with classification. If you see all the exercises all through the first part of the session, what we did was classification. You're trying to build the foundations, the fundamentals, and I think we have a very good understanding of classification by now, right? And when we talk about classification, we are only concerned about accuracy and the other confusion metrics related things, like so precision, recall, F1 scores, all of what we covered all through the prior sessions, right? So you look at a picture and you try to classify that, hey, what is the object in the picture? Okay, is it correctly classified? Now we have an additional component for regression. So classification, we are sorted. We can use accuracy, we can use confusion matrix, we can use precision, recall, F1 scores, all that. Regression, we will learn a new thing called IOU. This is a very, very popular way of measuring the performance of the model in object detection kind of problems, right? So IOU stands for intersection over union, and intersection over union basically means that, let's say we take an example, you have the predicted bounding box. This is what the model predicted, and you have the actual bounding box, which is the actual ground truth. Because we know, right, for all supervised learning problems, you have to have a ground truth. On one hand, the model will predict something. On the other hand, there is the actuals. This is actually what is the case. So there are two kinds of things you will have. You're always doing this predicted to actuals comparison. So here also there is a predicted bounding box and there is an actual bounding box. Intersection is this part, which part is overlapping, and union is this part, the overall. So when you divide the two, you get something called IOU. So IOU is a very, very popular metric that is used for object detection problems, where you are taking the intersection overlapping area and you're dividing it by the total area. Quite obviously, you can understand that if the predicted box and the actual box were equal, here it is not equal. Here the predicted is not completely overlapping with the actual. So there's a bit of error that is present, right? Okay, this is what I was referring to, that actually the dog is here, but the model predicted the dog to be here. There's a little bit of error that we can see. So naturally, if the predicted box is completely if it completely overlaps the actual box, then we will have an IOU value equal to 100%. So IOU equal to 100% means the predicted box will be exactly equal to the actual bounding box. So which is obviously an ideal scenario, which will never happen in practice. You can look at this diagram, which very beautifully summarizes all the different cases where we have different IOU parameters. You can see starting from left to right, you can see. So the extreme right-hand side part was the one that I was talking about. So the green is the actual box. The green is like the ground truth. It is like Y actuals. The red is the predicted box. Okay, so when you're analyzing these examples right now, you can think of the green rectangle as the actual bounding box. In the actual data, what is the exact position of the object? Because this has to be labeled initially, right? Somebody has to sit and label it. And the green one, the red one is the predicted bounding box. This is what the model predicted. And you can clearly see on the extreme right-hand side, the actuals are exactly equal to the predicted. The actual bounding box is completely overlapping the predicted bounding box, and that is the best case scenario that we are getting. So what is the best case scenario? The best case scenario is that the actual bounding box is completely overlapping the predicted bounding box. And what is the worst case scenario? The worst case scenario is the fourth one, the fourth case, where the actual bounding box is not at all overlapping with the predicted bounding box. And that is when the IOU is 0. So we see an IOU value equal to 0 for that case. So the actual bounding box you can see is not at all overlapping. There is no overlap you have in the predicted bounding box. So no overlap at all. That is a 0 IOU that you're able to see. And then you are able to see something in between. Like, for example, look at this one. This is like a 25% IOU. That means the actual box is 25% overlapping with the predicted box. And in the middle picture is where we have a 50% IOU, where the actual bounding box is 50% overlapping with the predicted bounding box. So IOU is a very good metric to evaluate the accuracy of a detection model. So there are two components. One is the accuracy part for classification. Obviously, that is more important because we have to classify the objects correctly. That is the most important metric. And the second part is the regression performance, which we can measure using something called IOU. So this is broadly how detection models are working. Now, what else? What else? What if I give you a slightly different problem? What if I show you this picture and ask you, where are the roads in the image? So far, we have done detection, and with detection, you can do a lot of use cases, right? So there are a lot of many of the surveillance use cases and photo camera based use cases, and they are all based on detection, right? But what if I ask you this kind of a question? Where are the roads in the image? Now, can you draw a bounding box to identify the roads? And if I ask you to identify the roads, can you just draw a rectangle to tell me, hey, I think the roads are here? So can you draw a rectangle? Can you draw a bounding box to identify the roads in the picture? Not possible, right? So you cannot draw a simple bounding box to identify all the roads in the picture. You will be unable to, draw a simple bounding box to identify all the roads in the picture. That will not be possible. So this is a very good use case of what we refer to as segmentation. So what is segmentation? Segmentation is drawing the exact boundaries around the object. Object detection, localization, what we talked about until now, we were drawing approximate boundaries around the object. You have a picture of an elephant and you're drawing an approximate boundary. You are drawing an approximate rectangle around that elephant and you're saying, hey, I think this is the elephant. That is detection. In segmentation, what you're doing, you don't want to draw an approximate boundary, but you want to draw an exact boundary, which tells me exactly where the roads are. See how we put this in red. We draw the exact boundaries around the roads and we explicitly specify exactly where the roads are. So that's the core idea, what we try to do in segmentation. Okay. Now there are a lot of practical applications of segmentation. So lot of good applications where segmentation comes in handy. So especially satellite imagery. If you look at this kind of a use case, we want to like something that Google Maps is doing. Google Maps is doing something very similar, right? You go to Google Maps and you have different layers, right? You can look at a satellite view and you can look at a default view. The default view is inherently using something called segmentation. That is how it segregates, parks, water bodies, and all that, right? So if you see, so all it's trying to do is, it is not giving you the approximate boundaries, not giving you bounding boxes, but it's actually giving you the exact approximations for where the roads are, where the trees are, where the houses are, and so on and so forth. So Google Maps will be a very good example of this particular piece. Let me show you an example. It will be good to see a small example in terms of what I mean to say. So all of you can see the screen here. This is, let's say, a simple example I'm taking right now, and you can go to satellite view. The satellite view will be the normal view that I'm taking, right? So let's say we're looking at a place called Kormangla. So this is Kormangla, and you're seeing lots of. We can look at a place where there's some rivers, it's not rivers, actually lakes. So we can look at this part, right? So um, this is the Mariwala Lake, and we have some parks here. We have some roads here. We have some houses here, and we should be able to get a very nice segmentation here. Let's see. So again, what is happening behind the scenes here is Google will look at the satellite image and it will try to, if you go to the default view, the map view, the default view, it will inherently do segmentation. So what it does, it looks at the picture and it tries to identify the exact boundaries of the different, attributes. So it's able to identify that this is a water body. It identifies these are roads, these are streets. So all the streets are with gray. All the parks are with greenery is with green, and any water body is with blue. Right now, the interesting part that you are able to make out here is that this is not exactly accurate, right? So this is completely based on approximation. It's done with segmentation. You can see, for example, here some part is a park, some part is a water. Is it correct? You can go to the satellite view and check. Maybe not. Look at it. It's not correct. So Google thinks this is actually a water. I mean, or maybe it's a swimming pool. Maybe most likely it is correct. Yes, it's a swimming pool actually. See, it identifies even that part very nicely. So it actually does it very well. It's a swimming pool and it identifies, it understands that, okay, this is a water body. But what about this one? What about this one? This one, maybe not. This is not a, I don't think this is, or maybe it is a water body, whatever. So it's actually, it's very powerful. It's able to figure out very nicely. But what it's not able to do is this part. Can you see? Like, this feels like, this is not water. Okay, the lake is here, right? The lake is here. Now, the human eye is able to decipher that, okay, these are deposits that are formed over the lake, right? If you look at the Mariwala Lake is actually here. But this is actually not the lake. This part is actually not the lake. But Google segmentation model says it is a lake. So these are some errors that you will find. And also the boundaries, they're not exact, right? If you see the lake ends here, but look at the tree lining. This is actually trees, right? This is green. So it's not able to do that. So just wanted to share with you that a lot of great practical applications, but is not 100% accurate. Okay, but very clearly, these are problems that are solved using segmentation. The only way you can do this is with segmentation. You can look at the picture and try to identify the exact boundaries of the picture. Another very good use case is the kind of background removal technology that we have today. So you use WebEx or you use Zoom meeting, Google Meet, and you try to uh, enable the camera and you try to remove the background from the image. So this is also a very, very good use case where segmentation models are used behind the scenes. So this is also an excellent use case of segmentation. What is playing out behind the scenes. This is what we inherently do in a kind of a segmentation model. So now how to perform segmentation, right? Very, very broad concept. The same way I explained object detection, in a very broad way, we understood it at a high level. What are the two components involved? There is a regression component, there is a classification component. Similarly, broadly speaking, what are the different components of segmentation? How do we do segmentation? Now it seems very complicated, but I mean, you'll see the architecture is surprisingly very simple. So when I show you the architecture, you will realize it is surprisingly actually very easy to do segmentation. So broadly speaking, what we do in segmentation is we do pixel-wise classification. This is all it is. On the left-hand side, you see the actual image. This is the simple picture of a cat in a park that we are seeing right now. And on the right-hand side, what you're trying to do is you're trying to generate the output. So you're trying to classify each and every individual pixel. This is what we are inherently trying to do in a segmentation model. You look at the original picture and you're trying to classify every single pixel in the picture. So we are trying to identify pixels which correspond to cat, pixels which correspond to grass, pixels which correspond to trees, and pixels which correspond to sky. You look at the original image and you look at each and every pixel in the image and you try to classify what those pixels are. What are those pixels which correspond to cat? What are those pixels which correspond to grass? What are those pixels which correspond to tree? And what are those pixels which correspond to sky? That's the crux of what we are trying to do in segmentation. There can be multiple classes based on howsoever many things you have. This is what we are trying to do. And if I show you one more image, look at it. On the left hand side, you have the actual picture, you have the actual image of cows grazing in a field, and we are trying to identify the different pixels in the image. So if you say this is a 100 cross 100 picture, so there are total 10,000 pixels, right? There are total 10,000 small pixels which comprise this image. And all that you're trying to do is you're looking at each and every pixel. So imagine there is a dense layer that we have for every pixel. So that's the way you can visualize it. So imagine for every pixel, so for each of the 10,000 pixels that we have right now, we have a dense layer for each of those 10,000 pixels. Think of it that way. We have a dense layer for each of those 10,000 pixels. So for every pixel, we are trying to classify that, hey, what is the probability it's a tree? What is the probability it's a cow? What is the probability it's a sky? And what is the probability it's a grass? So for each and every pixel, we are trying to classify what class that pixel belongs to. This is fundamentally what we are trying to do in semantic segmentation. This is the big picture idea. Now, how do we do it? There are different types of networks we use, and this is again back to CNNs and convolutional neural networks we can use. Anything that we do with images, these are just two different types of sub-problems that I wanted to show you. Apart from just classification, these are two other areas that we have. And segmentation is very popular. If you're looking at semantic segmentation, this is extremely popularly used in areas pertaining to, as I said, like even healthcare. Where you look at an X-ray, you look at an X-ray and try to identify what are the different problem areas in the X-ray. Let's say you're trying to do some kind of tumor detection or cancer detection. Okay, you're looking at the picture of an X-ray and trying to identify whether you're able to spot any tumors or not, whether you're able to spot any cancers or not. Okay, so a lot of healthcare use cases employ segmentation because you want to be very accurate as to the exact boundary of the tumor. By looking at the X-ray, can I pinpoint exactly where the tumor is occurring? Because we cannot do a rectangular box. Rectangular boxes can be inaccurate. It doesn't completely capture the boundaries perfectly. So segmentation has real use cases in some of these, radiology use cases and also even pathology use cases. Okay, it's a very growing field. Healthcare is a very growing field where, especially imaging applications, it could be radiology, applications or even pathology applications where you study a sample, a blood sample under a microscope. You look at cellular level data and and doing segmentation at a cellular level. There's some very very cutting edge applications that are playing out in that field actually. Okay, otherwise segmentation is very expensive. So unless there is a very very dire need, like in healthcare, there's a dire need because you need accuracy. It has to be 100% accurate or at least very close to 100%, or even self-driving cars. Self-driving cars are also a very good application area where segmentation models must be used, because you have to be exactly accurate in saying, in determining the contours of a person. You cannot just put a rectangle and say, hey, I think the person is here, because the rectangles can be highly inaccurate, right? Or let's say footpath, or let's say trees, signboards. You cannot do detection there. You cannot just put a rectangle. You need to exactly put a boundary around that object. So segmentation is very very powerful, but segmentation is also very very costly, and you will have to select your use cases. And like for example, many of the surveillance use cases that we have. Okay, if you look at store surveillance and city surveillance, company surveillance, you're using CCTV cameras and machine learning is happening there, right? So they are not using segmentation because they don't need to. If you think of the use case, you don't need to identify the exact boundary of the person, right? Imagine you have a surveillance camera that is running at night, and you just want to identify detection, and you want to identify that, hey, if I see a person appear at night, I will ring an alarm. Maybe it's a very secure data center that you have, or a very secure server room, and you have a camera that is enabled. And if it senses a person, if it detects a person, the alarm will ring. So the use case is only detection. The use case is just to identify that frame where the person is coming. You don't have to capture the exact boundary of the person, right? That's not a use case. So you don't need to do segmentation in many cases, even for road traffic cameras and all that. If you see city surveillance cameras, most important use case is detection. You have to be able to locate a person and form a bounding box around it. Form a box around it. Even if it is inaccurate, it's fine, but it gets the idea. It's not a mission critical case that you have to exactly locate the exact boundaries of the person. So defining the problem statement is very important. See what I'm getting at? So it's very important to understand what you're solving, what problem you're solving, and based on that, you decide on the strategy, decide on how we will approach it, how we will solve the problem, and all that. So that's about segmentation. I hope everybody has a very good sense of the different subfields of computer vision. What are the different things we do? It's not just classification, but there are multiple other things that we do. And this was to give you a very, very quick understanding in terms of what are the other fields that we have in the world of computer vision, right? So now what we will do is we will enter into one more very interesting type of data, which is referred to as sequential data. So all this while we have discussed quite extensively about structured data. We have discussed quite extensively about images. We have discussed quite extensively about different forms of text. Now we will talk about another kind of data called a sequential data. So what is a sequential data, and what types of neural networks are used for handling sequential data? Right, just like how we discussed about CNNs, convolutional neural networks are very popular while working with image kind of data. So similarly, we use an architecture called RNNs or LSTMs, which we will see now. We will broadly talk about LSTMs here, what LSTMs are and what type of data domains they are used in at a very high level. So what types of problems are solved using recurrent neural networks? In other words, we will learn about a slightly new kind of neural network right now, very quickly. We'll just take another 15-20 minutes here. First, talk about what type of data we have, what is different about sequential data. First, talk about some example problem areas involving sequential data. Second, we will identify what are the limitations of using dense layers. Why can we not use a normal neural network for sequential data? And number three, we will introduce RNNs and what RNNs bring to the table. Okay. So sequential data, as the name suggests, is any kind of data which follows a sequence. Very clearly, sequential data is a kind of data which follows a sequence. A very good example could be text data. We've discussed about text data day before yesterday. We looked at applications on um, sentiment analysis. We looked at review classification. If you look at text inherently, text is inherently a kind of sequential data because every word that you use in a sentence or the sequence of words that you use in a sentence, there is always some relationship, right? So you're using different words in a sentence. First, you're using word one, then word two, then word three, word four, word five. So as we use different words in a sentence, the sequences are kind of linked or related. So first you're using word one, then you're using word two, then word three. The words are not getting used in a haphazard way. There is a sequence in which the words are getting used. So text is inherently sequential data. Another good example is audio, musical notes, audio, any kind of speech patterns that you're using. That's also sequential. Because when you listen to an audio note and some kind of music or audio, whatever, it could be speech. Speech is also audio, right? So if you convert it to a numerical form and if you study that, the audio waves, they follow some sequence. Another excellent example of sequential data is time series. Time series data is another very good example of sequential data. If you look at stock market performance of a company, let's say you look at some company XYZ, you look at BSE Limited, and you want to study uh, the stock performance of BSE Limited over the last X number of years. Okay, how has BSE Limited performed over the last X number of years? If you look at the stock performance of the company, that is again a very good example of sequential data because every data point, imagine every day is one row. So this week we had Monday to Friday. So Monday, what was the stock price? Tuesday, what is the stock price? Wednesday, what is the stock price? If you look at the last 4 days worth of stock data, stock price data, that is a sequential data, right? Because Tuesday's data depends on Monday, or rather, I should say depended. It's in the past. Wednesday's data depended on Tuesday. Okay, then you had Monday, Tuesday, and Wednesday's data, and that is used to find out what is third. So the next day's data, to some extent, depends on the previous day's data, right? So that is sequence. If you look at a sentence, you write 3 words in a sentence. Ram is a good whatever. So the fifth word that you write will somehow depend on the first 4 words. The important concept for sequential data would be that they are not independent, right? I'll give you one more analogy to help you think about it very nicely. Look at all the types of examples we have seen so far, structured data, right? So if you go back to the very first use case, we did an advertising case study, iris regression, right? Loan default prediction, all of that. Every row of data is independent of the other rows, right? Think about it. Go back to the iris data set. We had 150 different types of flowers, right? Sepal length, sepal width, petal width, and we are trying to predict what is the class of the flower. That's broadly what we are trying to do. So if you look at that kind of data, each and every row in the iris data is independent of the next row. They don't have a relationship, right? If I give you row 1, row 5 has nothing to do with row 1. The observations have been collected independently, right? If you look at the diabetes data set, we had every row is a person, right? We have the different attributes of the person, blood pressure, glucose level, and trying to predict diabetes. The rows are not depending on each other, right? Think about it. That is non-sequential data. All of what we have done until now is non-sequential, right? Or if you look at the recent example, the one that we discussed just an hour back, the flower classification. Every row is a flower. You have different examples of flowers. Daisies, dandelions, roses, sunflower, tulips, right? Every row is a flower. Is there any relationship between example 1 and example 7? None of it, right? You're just independently showing the machine different types of flowers, right? You're showing it a picture of a rose, showing it a picture of a daisy, But there is no sequence, right? It is not that if I show you the first 6 pictures, you will somehow get better in the 7th picture. No, there's no sequence. It's completely independent, right? Even if I shuffle the rows, even if while training the model, if I shuffle the ordering of the rows, nothing will change. This is very important, friends, okay? Even if I shuffle the ordering of the rows, the accuracy will not be impacted. That's a non-sequential data. But when I talk about examples like speech, text, audio, time series, these are sequential data. Why? Because there is a relationship between row 1 and row 2. Only after Monday has happened, Tuesday can come. Tuesday cannot come before Monday. Depending on Monday, Tuesday, something else will happen. Depending on Monday, Tuesday, Wednesday, something else will happen. So the next rows in the data are inherently dependent on the previous rows. That is sequential. The same applies for text data also. When you write a sentence, the subsequent words in a sentence, they go back to the previous words in the sentence, whatever you use, or maybe some other past sentences and all that. Okay, so that's the whole idea of sequential data, and this is the kind of data that our traditional neural networks cannot handle. So we cannot use a ANN model. ANN model stands for an artificial neural network. So we cannot use an ANN model to work with sequential data. And we cannot use a CNN model because CNN is used for computer vision. We cannot use a CNN model to use for sequential data. So we use a new kind of neural network called recurrent neural networks. Just keep this at the back of your mind. We will not go to the theory in detail, but at a very high level, recurrent neural networks are a special kind of neural networks that have memory. Okay, so they are a very special kind of neural networks that have memory. You are somehow able to remember what happened in the previous steps. Our existing models that we saw, they are not equipped to remember the previous. But ultimately, the broad idea is still the same. You still have neurons, you still have hidden layers. Nothing changes there. The concept of neural nets don't change. Nothing changes. You can simply think of RNN like a block. The same way that we use something called Con2D, you will use something called RNN. That's it. I mean, from the practical hands-on implementation, nothing will change. But conceptually, what is different about a recurrent neural network? What is different about this architecture? They are able to remember the past inputs. Like unlike a CNN where you just give a picture and it processes only one picture, the RNN, what will do is it will somehow try to remember the past sequence. Right? If you have a time series data and you have got the last 30, 40, timestamps, it will somehow retain that information. It has memory. The important takeaway is it has memory. RNNs have memory. The other neural networks that we have discussed so far, they don't have memory. The RNNs remember what happened before inherently. So as this idea developed, we had a very new set of architectures that started coming out called sequence to sequence models. This was this enabled us to do a lot of incredible things. We were able to all of a sudden look at documents and start summarization. I know summarization is it's a very obvious thing we're able to do today with Gen AI, but even before this, we were able to do summarization long before Gen AI. So we were able to do summarization using LSTM and RNN models. Okay, so using recurrent neural networks, we were able to summarize very effectively. And if you think about it, there's a sequence, right? Documents are text data. There's a sequence. It's sequential data. Even summaries are sequential data. So this is the sequence to sequence model. What is sequence to sequence? That means you're using one sequence to predict another sequence. Sequence to sequence. Another good example of sequence to sequence model will be this one. Look at this. This is image captioning. You look at an image and try to predict a text. Even an image can be thought of as a sequence of pixels, right? You look at an image which is a sequence of pixels, and based on the picture, you try to predict the text. Or language translation. This is one of the earliest examples of sequence to sequence model. You give me a particular text in some language, and I will predict another text in some other language. So this is again a sequence to sequence model. Or another very good example could be email responses. Okay, so how do we look at a particular email, the text in the email, and based on the text in the email, can we predict the corresponding response? So you give me one sequence as input, and I will generate another sequence as output. So this is the use case that we are talking about. This is sequence to sequence model. Now, at a very high level, how do we do it? I'll just talk about the high level, how it's done. We use something called an encoder-decoder architecture. And at the core of it, we will use a new kind of neural network called recurrent neural networks. This is what I was mentioning. So we use something called RNNs because RNNs have memory. RNNs are able to remember the context. Using recurrent neural networks, you are able to remember what happened in the previous steps. Okay, so whenever I use the term RNN, remember there's another term that will often get used along with it. It's called LSTMs. LSTMs are a slightly improved variant. It's a better variant of an RNN. RNN is a very generic term I'm using. There are a lot of problems with RNNs, which are mathematical, like vanishing gradients and all that we'll face. So instead of using RNNs directly, you will use a slightly different variant of RNN called LSTMs generally. But both of these are used interchangeably. Or GRUs, another term that is used is GRU. The next time you see any of these coming up in slides or hands-on or any of the exercises, just remember we either use RNN, the actual Keras short form is RNN, we will use RNN, which stands for recurrent neural network. Either you can use RNN, which is the plain vanilla, the very broad term, or you can use more specialized variants of RNNs called LSTMs or GRUs, which are more popular. These are much more popular and much more best practices that we have. Okay. So we take an input sentence and we try to use an encoder model to generate the encodings. This is what we did here. You can see we take the input sentence and we use a recurrent neural network to generate the encodings. This is right at the core of what we talked about in word2vec, right? All of you recall that word2vec where we talked about sentence embeddings, right? That's all that we are doing, just that we are doing in a better way. Word2vec was the traditional way how we were doing it. This is where we are using a neural network. In word2vec, we were just using a pre-trained model, but here we are building our own recurrent neural network and we are generating the sentence embeddings. And the second part is using a decoder where we decode it back to the corresponding Hindi sentence. This is the big picture idea. So we have got two important networks that are working out here. That's the big idea. On the left hand side, we have an encoder neural network, which is an RNN, which is used to take the original sentence and encode it into a numerical form. That's what the RNN is doing. And once you get the encoded representation, we are using another neural network to take that input and generate the output Hindi sentence. And that's a sequence to sequence model. And why are RNNs used again? Because the sequence is important. We should remember how the words are coming. So why are the RNNs important in the decoder? Because again, while generating the words, it is important to remember the order of the generation. So the RNNs will remember the order of generation. So wherever you're either working with input sequences or output sequences, RNNs are mandatory. Or as I said, instead of using RNNs, you will use LSTMs or GRUs today. So let's go to Delhi. Aao hum Delhi jai. It's able to generate these kinds of predictions. So this is what we call an encoder-decoder architecture. So this is the big picture idea. And this is what we call a sequence to sequence model. Right? I hope everybody has an idea of this now, a good idea. And this is how you will implement much of the real world use cases that we talked about. Like if you have a text to text, let's say you have a input text and you want to generate a summary. Again, same way, same idea, sequence to sequence. You give an input text as input, the encoder will encode that and the decoder will generate a summary out of it. Okay, but you have to remember this is all rooted in supervised learning. So for you to be successful in doing any of this, you will have to have lots and lots of label data. This is back to the foundations of supervised learning. So you will have lots and lots of input output sentences. So for Google Translation to work effectively, so somebody will have to give the machine lots and lots of label data. Somebody will have to give the machine, as you can see, lots and lots of label data. So we have lots and lots of pictures of what, lots and lots of images of what, so you've got lots and lots of examples of the original input sentences, and you also have lots and lots of examples of the actual Hindi, the Hindi outputs, or whatever outputs it could be Hindi or some other outputs that you might want. So take the data, take the original data, whatever we have, and based on that you do supervised learning. Okay, you try to learn the weights and biases. in the network so that you're able to, the predicted values are equal to the actual values. That's the crux of what we are trying to do. So we are trying to figure out the weights and biases of these neural networks. Okay, this is the neural network 1, this is the neural network 2, and you're simply trying to do gradient descent. You're trying to fine tune this network so that you're able to accurately predict what the output Ys are. But this is back to the foundations of supervised learning. Okay, and this you can also extend to intersections of computer vision and NLP. Like this is right now all that we discussed was sequence to sequence models in the context of text. So until now we covered only sequence to sequence models in the context of text. But what you can also do, you can also uh, look at sequence to sequence models in the context of images. So what could be an example of a sequence to sequence model in the context of a picture? Let's see that. So this is a beautiful example of an image captioning model. All of you can see. This is a very good example of an image captioning model. Everybody can see the screen. On the left-hand side, you are using an input picture, and based on the input picture, you are generating a description of that picture. And this is architecturally how it's happening, right? So the big picture idea is we have the input image on the left-hand side, and based on the picture, we want to generate the description. And you might be wondering that, hey, why would somebody ever want to do that, right? Why would somebody want to generate a description of a picture? Well, it could be very useful for blind people. And we already have this kinds of cutting edge technology today where there are glasses, all these research happening like Meta and Ray-Ban, there's that, and even Google is coming up with a partnership with another company, and they're coming up with that Google AR glass, right? So lot of innovation is happening in the smart glasses space. And the modern smart glasses that we have today, like the ones that Meta and Google are working on, those smart glasses, they have inbuilt cameras, like you wear spectacles and they have both. They have powered prescription and non-prescription lenses. So like those lenses are like virtual screens. One is you can see normally like how you will see through a lens. Second is they will also embed other kinds of information in the lens. Okay, or there'll be inbuilt speakers that will read out, but there'll be small cameras that will be inbuilt on the frame, not the lens, obviously. On the frame, like the spectacle frame, you will have small cameras. Small cameras will be embedded, which will see what is there in front of you, what is there around you. And it could be very useful for a blind person. Let's say like the model could see a picture, it could take a real-time image, 360-degree view of what is around the person, and it could basically describe and read it out for the person because the person is unable to see, right? And even for augmented reality AR applications, it will be very useful. So not always are we able to make out what's in front of us. And this kind of technology is also very useful in the military, in the army, where cutting edge equipment, helmet mounted displays is what they call it, right? So you can look at helmet mounted displays where based on the picture, the displays will identify different components and read out threat levels and all that. But this is the core idea. This is the core idea. Technically, what do? We take a picture, we pass it through a CNN, we extract the features, we generate the features, and whatever feature vector we are getting, now on the basis of that, we will pass it through the LSTMs and generate the output. This is the idea. So, in case this looks a little complicated, you can think of this as one block. Don't worry about the LSTMs and all. This is again not really something we're interested in right now. But you can think of this as one big block. This whole thing is LSTM or RNN. So take the picture. Excuse me. This is the encoder network. The encoder network will encode the picture, and then it will pass it to the decoder, and the decoder network will generate the output words. That's what the encoder-decoder architecture will do. The encoder will take the picture and it will encode this as a feature vector, and the feature vector will be given to the decoder. The decoder will take that feature vector and generate the sequence of words. Okay, so this is another application, and you can reverse this. You can actually reverse this and also look at a text-to-image use case. The ideas are very similar. Okay, so there are a lot of applications we can talk about when it comes to especially sequence to sequence models. Another very good application could be customer support, the kind of thing that is so common today, so commonplace today, rather. So we can extend this conversation to customer support, and we can look at something like this. Look at this. How do we go and how do we do this with tech support? So customer asks a question that will go to the encoder model. The encoder model will encode the customer question in a sequence of numbers, and that will go to the decoder model, and the decoder model will go and generate a response. So this is at the crux of what is happening in an encoder-decoder architecture. So when you talk about encoder-decoder architecture, this is fundamentally what is happening in encoder-decoders. Okay, so the encoder model will take the original picture, it will generate this, and the decoder model will go and it will generate the output responses. That is fundamentally what the decoder model will do. Now, if you think about it, this was around 2014 and 15 when the sequence-to-sequence models really started, really started flourishing around that time. And what happened after that was we had in 2017, there was a paper that was written. So 2017, there was a paper that was written, and there we had a very, very popular idea called transformers were discussed. Okay, so 2017, there was a paper, and in that paper, in in 2017, the idea of transformers was proposed. So the name of the paper was "Attention is All You Need." It was a very, very famous paper that was written in 2017, and in that paper, the concept of transformers were proposed, and transformers became an absolutely, revolutionary idea from then on. Okay, now these are again very, very advanced topics. We're not going to be getting into this in a lot of detail, but just to let you know what is a transformer at a very broad level. What is a transformer? This is what a transformer actually is. This was 2017. 2017 is when this was proposed. Okay, and what is a transformer? Now that we understand encoder decoders, you can see transformers are nothing but they are extensions of encoder decoder blocks. There are obviously more ideas that are present, but this is at a very high level. You are basically stacking multiple encoders and you're stacking multiple decoders as in an ensemble. The same way that we create stacks of neurons and create a neural network. So here it's like a think of it like a stacked encoder decoder architecture. At its core, it is based on encoder decoders. You're having some encoder network that is encoding the original input text or input whatever. It can be text, images, whatever. And there's a decoder network that is decoding that intermediate thing into some other output form. That is what the encoder decoder is doing. And what is transformer? It is stacks of multiple encoders, multiple decoders. As per the original paper, they proposed 6 encoder-decoder pairs, and there are different variations of it. This is what it's doing. And this was 2017. And as you know, all of you know from there onwards, 2018 is when OpenAI came up with their very first GPT model. The GPT version 1 was released in 2018. So 2018, two very good things happened. One, OpenAI launched their very first version of GPT. We didn't have any language models back then. That was the very first language model. And obviously, there was another very, very close competitor, Google. Google had a BERT model. So BERT also was a transformer-based architecture, BERT, bidirectional transformer-based architecture. And as we know it, ever since transformers came out in 2017, the entire world of deep learning has changed. We were able to perform tasks with more accuracy. It is not as if we have some very novel, problem statements. The problem statements have always been there before. Like if you look at language translation, it is not that language translation is something new. We have been doing language translation for decades now. Even if you language translate was even there 10 years back, 15 years back also your language translate. Google had language translate 10 years back. It was there, but it was not efficient. You had Google Assistant even 10 years back. You can say something, it will convert it to speech, but it was not efficient. Okay, Google has been a feature that's been there for a long time, but the same way it can efficiently pick up what you're saying, it was not that efficient maybe 10 years back, right? So transformer has been a very revolutionary concept in terms of how we are able to achieve things today. And this is at the core, what you're seeing on the screen, this is at the core of how large language models are built today. Starting from the very first model, GPT version 1 by OpenAI, 2018. And GPT, the term GPT also, if you see, what does GPT stand for, friends? GPT stands for Generative Pre-trained Transformer. That is what GPT stands for. At its core, it's a generative model. It's a pre-trained model. So we talked about transfer learning. So there's some amount of pre-training, and it's a transformer-based model. So the term GPT stands for Generative Pre-trained Transformer. And then after that, as we know the roadmap, 2019, 2020, we had GPT version 3, 2022, GPT version 3.5 was released, and December of 2022, as we know it, ChatGPT was born. ChatGPT was inherently based on GPT 3.5. 2024, we had GPT-4, GPT-4 Omni, and 2025, as we see in this year, a lot of innovations have happened. They have released GPT 4.1, GPT 4.5, and these are all iterations of GPT, as you can see. So fundamentally, they are all based on transformer architecture. And you look at all the top language models today, Anthropic, Cloud A, if you look at, they're all inherently transformers. Why? Why is it so? Because what is transformer? If you unravel and think in a very simple way, in a very, very high level, if you look at it, what is it? Encoder, decoder. And if you look at what these language models are fundamentally doing, what are they doing? You go to ChatGPT, you ask a question, you get an answer, isn't it? That's what they are doing. That is what these language models are doing. You give it some question X and it is giving some output Y. Okay, so think of this like your large language model. Think of this like your ChatGPT interface. You are asking some question input. It is generating the embeddings of that question. It is converting that to a sequence of numbers, which is fundamentally based on word-to-vec and embeddings that we discussed. And then the decoders are generating the answer. That's the crux of what's going on. Okay, so I hope you're able to build that. Everyone's able to understand the chronology. So part of this discussion was to help you with the chronology as to what happened, how things progressed, and where we are today. So we did not end up today by chance. There's a lot of background. There's a lot of history that went behind, right? So when you talk about generative AI, it didn't come all of a sudden, right? The earliest neural networks, the earliest applications of generative models were there in 2014. So GANs are also not a new thing. Generative models are not a new thing at all, just to clarify. I mean, again, this is a different topic, but just to let you know that the earliest generative models were proposed back in 2014. And there was a person named Ian Goodfellow who came up with the very first iteration of a GAN. So GANs stand for Generative Adversarial Networks. This is what GANs are, okay? Again, it's a different topic. It's another conversation for another day. But just to let you know, the very first generative models were proposed back in 2014 by a person named Ian Goodfellow. And today we are obviously, there are better ways of doing it. It is not to say that the problem statements are new. So we had these problem statements for a long time. We wanted to create pictures. We wanted to generate text, generate audio, but the capabilities weren't there. The hardware wasn't there. The architectures weren't there. So we have come up with better approaches. Transformers has been a big revolution. We didn't have transformers back then. Although it seems like a very easy concept, but that's the nature of discovery, right? So you come up with better ideas, and we are able to do things in a better way today. Okay, all right. So this was just to give all of you a very broad understanding in terms of what's possible, what are the different things, and I hope everyone at this point in time has a very solid understanding of the different components of deep learning, right? Again, it's a very short span of time we had where we tried to give you a very big picture idea of different things. I'm a firm believer the code is really not important. Like, although we have done some coding, but honestly, you can generate code, you can get code from hundreds of sources. But what is really important is the understanding the concept, understanding what is what. And I hope this particular discussion has helped you, like at a very high level, understand what deep learning is. What are the things we can do? What are the broad areas that we have? And how the different areas are connected. So this pretty much covers all the aspects of pretty much what you have, even going to Gen AI.